If anyone else want to say anything
anyone else want to say anything more?
Otherwise, I guess Sebastian could
could start.
Yeah. Sebastian from the University of Oxford. He is talking on a selection of observations in conflict with ΛCDM. Actually, this is the first session where we discuss observational tensions in astrophysics and cosmology. So the speaker has 40 minutes for presentation and 15 minutes for discussion. So Sebastian, please, over to you.
Okay, thanks very much. Thanks very much for organizing and for introducing me. I'm going to give a short overview while I look for my slides. I think that might work. Do you see this? Okay. Can you see the slides all right?
Yeah.
Yes, great. Okay, so you said 40 minutes of a talk and 15 minutes questions. That's fine by me. I was told 30 minutes of a talk and 25 minutes questions. Either way, you're welcome to ask questions.
Yeah.
Yeah, but either way, you're welcome to ask questions during the talk as well as after. So we can put anything. Okay, so Internal asked me to give a talk on selections of observations in conflict with ΛCDM. This is not a complete overview of all of the observations that may be in conflict with ΛCDM, of which there are, of course, some in sort of every range of physics or any type of question you could ask. And you'll see during the talk sort of what I will be focusing on. And I think Internal and some of the other talks are going to pick up other problems. So I want to start with something that I often start with. So this conference, if it had been held 500 something years ago, could have been called CMC Challenges to Modern Cartography, which is something that is maybe topical because just earlier this week in the US there was the Day of the Indigenous People that commemorated the disorientation of Columbus back in 1492 when he arrived at the Bahamas believing it was India. So if we do go back to that time, and this is indeed 1942 when this globus on the left was made, the idea of how a map of the world might look like was like this. So on the right hand side you see the globus sort of wrapped up or wrapped open. This was indeed the first globus that was made, the first map of the Earth that was put onto a sphere. And so in order to know how to map the known continents at that time onto the sphere, one had to know how large the sphere is or how large the circumference of the sphere is. And as you see on the right-hand side, it doesn't look like there's much missing, right? I mean, obviously we know of the oceans, but it doesn't look like there's a big gap in the map of where something at that point unknown might still be placed. But of course, we know that an entire continent, the entire Americas, were missing on that map. And this is due to the fact that map makers of the time had assumed a measurement by Ptolemy to be correct, which assumed which stated that the circumference of the Earth was about 30,000 kilometers, which was, of course, 25% less than what it should have been. It's funny to state that actually an earlier measurement by Aristophanes had correctly obtained 40,000 kilometers, which for that time actually is quite an achievement. And also an earlier measurement of Ptolemy himself had stated 40,000 kilometers, but those were largely ignored. So based on the assumption that 30,000 kilometers was the circumference of the Earth, all of the cartographers, built their understanding of the world to that date. Going forward, and so that only was then challenged with the discoveries of more continents, and of course the understanding of the world and the understanding of maps had to be adjusted from that point onwards. So, of course, we're not in the 15th century anymore, so we have to challenge modern cosmology as opposed to cartography. But maybe the idea is a bit similar, that, of course, we could come up with a different theory or come up with different assumptions, but in the end, it all has to match observations. So selecting observations that are in conflict with our current model is something that's really valuable, I find. And so that's what...
Recording in progress.
That's what I'm going to speak about here. I can't remove this. Let me unshare for a second and agree that the recording is in progress. Oh. Here we go. Sorry about that. Okay. If we want to challenge ΛCDM or judge whether an observation is in conflict with an ΛCDM, we should be able to define ΛCDM first. And of course, you know that ΛCDM is not just ΛCDM. Of course, there's a whole host of assumptions and sort of relations between different concepts that are behind what we call the ΛCDM model, or the standard model of cosmology. And after I've done so, I will turn to some of the recent challenges in ΛCDM, and specifically those that are to do with sort of the discrepancy between local and global observables. And I think by that time the 30 minutes should be up, so then I'll provide an outlook, and I'm looking forward to discussion. So we start constructing our standard model of cosmology based on something that is fairly simple. We want to make it the simplest possible assumptions given a couple of observations that we had. And these assumptions were made 100 years ago. Right? General relativity had been invented and or discovered, and the Friedmann-Robertson-Walker metric, which is the metric to the top right, describes a maximally symmetric universe that has a spatial part that expands with cosmic time. The maximal symmetry is, of course, one of these assumptions, these simplifying assumptions, but it is one that serves us pretty well because it makes us able to solve the Einstein equations quite easily. So in order to solve the Einstein equations, we also need to plug in an energy momentum tensor. And this energy momentum tensor could be one of an ideal fluid, which is usually assumed, which itself has to be composed of the different contributions to the energy density. So these are the usual ingredients of radiation and matter, cosmological constant and curvature and so on. So assuming that we have now counted all of the available contributions to the energy density, like in the lower line, we say they all have to sum up to 100%. And so this is what we call the cosmic sum rule, which then helps us to interpret observations of different kind, which I'll show in a bit. So really, ΛCDM is a model that is not just lambda, the cosmological constant, and cold dark matter, but it assumes all sorts of things. Right? So at first, we base everything on the validity of general relativity. Once we've done so, we pick a suitable metric, which in our case is the Friedmann-Lemaitre-Robertson-Walker metric. Then, as I said, we have to decide on the energy budget of the universe, and this could be lambda and CDM, but then also baryonic matter, because we know we're made of it. Possible curvature, radiation, other light degrees of freedoms. Of course, we know neutrinos, but maybe there are other quantum fields that contribute. And lastly, that alone doesn't really help. Of course, we need to form structure. In order for structure to form, we need to perturb these energy densities already early on. So we assume that adiabatic perturbations, specifically Gaussian perturbations, are seeded by a primordial Pau spectrum that itself would have been produced by the random fluctuations during inflation. So all of these ingredients make up the standard model of cosmology. And of course there's more, because in order to describe specifically how galaxies form, and so we need to discuss those processes, and so there's a lot more physics that goes into it. So a challenge to lambda CDM, where lambda CDM is taken as a variable of the standard model of cosmology, could be a challenge to any of these, right? And so that makes the question quite difficult. Okay, lambda CDM is a model that is based on these assumptions, but how well does it? Of course, we know it does extremely well, right? So on the left-hand side, I show you one of the examples where it does pretty well. A set of CMB power spectra, the temperature and the polarization, also in cross power, and the lensing and power spectrum on the bottom right. And the lambda CDM model predicts this blue line that we see that goes extremely well through all of the data points, from very large scales on the left to very small scales on the right. So already here, of course, we include a couple of assumptions on exactly how matter and radiation interact and all of these things. But the nice thing is that we can really describe these observations of their very early universe with just 6 parameters. So the top 6 parameters in this table are those that I just meant, and Plick is the likelihood of describes their best fit value. The right-hand side is just is using other likelihoods. The parameters below the central line are derived parameters. They depend on the parameters above the line. And so those are, of course, some that one can use as a prediction of the CMB and then compare against other measurements of the same parameters using other observables.
Sebastian, can I just, I think you said we can interrupt, right? I think you said that. Right?
Yeah, absolutely, please.
Yeah, nice to see you. And I just wanted, because you used the word lambda CDM predicts this, right? So, but that is strictly not correct. You can say it accounts for it extremely well after the parameters have been fit, after the model has been fitted to these observations, right?
Yeah, that's correct. That's a fair remark. Lambda CDM itself, of course, has free parameters. So as long as those free parameters are not fixed, it can't predict anything. It's not like this comes from first principles. It's a parameterized model, and you need to know what these parameters are. So these observations fix those parameters, and you're right to say that the observations given fixing of those parameters can be described well by this model. Does that work? Yeah. Okay. So, but there's more, right? There's not just these 6 parameters. I want to focus, for example, on these 2 here. So AS and NS is AS is the amplitude of scalar fluctuations, and NS is the spectral index, or the tilt of the spectral index of the power spectrum of these scalar fluctuations. And so that normally is assumed to already have a parametric form, which is a scale-independent power law. So that can be attempted to be measured. And so on the right-hand side, I show you some reconstructions that try to attempt to derive, these red lines, or the line that seems to be constrained from within the red area, from the blue line that we see on the left. And there are some assumptions in here, so it doesn't allow for completely wild power spectra, but it does appear that, for a large range of scales, this is indeed a scale-free power law. And this is what I meant earlier, is predicted by inflation. That it should be, it's predicted by simple models of inflation that it should be scale-free. But of course, if you were to invoke more complicated models of inflation, you would have maybe features in this power spectrum, and those features would translate into features on the left-hand side in the power spectrum of the CMB. So there are a couple of, what I'm saying is that there are a couple of sort of hidden layers in what we refer to as the lambda CDM model, and each of these layers could be scrutinized, of course. Okay, so another piece of data where lambda CDM fits exquisitely well are baryonic acoustic oscillations. So here I show results on the 2-point correlation function. So this is in real space now, a measurement of the fluctuations of the large-scale structure as traced by different galaxy samples. The top panels and the middle panels show exactly this. So this is a small range of scales where we see a feature which we call the baryonic acoustic oscillation feature that translates immediately to the wiggles of the CMB. And you see that again, the data points are pretty well described by the line. In fact, we see two lines, one is pre and one is post reconstruction. If you want, you can ask me about this, but in this case, even pre-reconstruction fits quite well. And another nice prediction of the perturbations that we see is, of course, that we have perturbations in the peculiar velocities, which lead to redshift space distortions. And the redshift space distortions lead to a non-zero higher multiple moment in the two-point correlation function. So that is what you see in the bottom panel, where you see not chi0 of S, but you see chi2 of S, which is the quadrupole of the two-point correlation function. So you basically do a Legendre transform. Legendre polynomial, sorry. Okay, so that fits quite nicely, and that is because Daisy was able to obtain so many spectroscopic redshifts, which is, of course, something that's quite recent. Okay, so if we want to compare the CMB measurements, and this is just one of the many different plots that one could show, with the BAO measurements, in this case I show the plane of omega m and omega lambda. Omega m, you may have remembered, is something you could see in this table I showed you before. Omega lambda you didn't see because lambda, of course, didn't have an effect on the CMB at those early times. But the cosmic sum rule helps you obtain also a value for omega lambda, which is why the CMB measurements translate to this gray line, or this very thin ellipse in the right-hand plot. And the BAO measurements that are shown to the left, in fact, these are not exactly those. These are EBOS measurements, but still they're quite similar, land quite closely to, in this parameter space, quite closely to the ellipse of the CMB. And another ellipse that I show here, but which I won't discuss in all too much detail, is a measurement that you can obtain with supernovae, where supernovae are very low redshift compared with the other measurements, and they too appear at a similar point in this plot. So that all is huge support to the lambda CDM model as something we now call the cosmological standard model, and it serves us well. I mean, it is able to describe quite a broad range of different observations. So instead of going more into observations, I want to go back to my list of ingredients, and of course any point in this list could be questioned in any possible way. Of course, general relativity may need to be modified in order to account for some observations that we're yet to make. The FLRW metric might well be replaced with a different metric, or maybe if we lived in a different topology, one that is more curved than the one we think we live in, we might need a different metric as well. The energy budget itself could be questioned, of course, and we could invoke contributions to the energy density that are other than those that we count so far. That could be anything from axions to back reaction or any of these proposals. And the perturbations themselves could be non-Gaussian as opposed to the Gaussian ones we assume. They could be isocurvature. We could have scale dependencies in the primordial power spectrum. Or we could have a mixture of adiabatic and isocurvature. There are all sorts of different variations that we could consider. And of course, if we say the primordial power spectrum was seeded by inflation, then alternatives to inflation or more complicated inflationary models would predict differences there too, which of course propagate all the way to the observables. Okay, so many of these are theoretical considerations, and of course one could cook up different theoretical models, which is of course interesting in its own regard, but it's hard because the lambda CDM model does fit exquisitely well, and coming up with a just one of the many other theories that could fit that then does fit is quite magical. So maybe an easier way to obtain an understanding of whether the lambda CDM model is the one we should go forward with is just performing consistency checks. So again, the observations like observing that the map of 1492 was in fact inadequate to describe the world. So one such consistency check is something that is called the Hubble tension. The consistency check is the following. We measure a Hubble parameter based on the CMB, and we may measure a Hubble parameter based on a more local measurement, in this case, maybe supernovae. And according to the model as such, these two measurements should be the same. And it has emerged over the last 10 or so years that these two measurements, in fact, are discrepant, and they're discrepant now at around 4 to 5 sigma. What I show here as well is another measurement, also local, so just like supernovae, but just calibrated in a different way. So instead of Cepheids, you calibrate them with tip of the red giant branch measurements, and this is something that Wendy Friedman is pushing forward, where you see yet a third measurement in between these two. So the Hubble tension has been occupying us for quite some time. But okay, so this is an example of a comparison of an early time and a late time measurement, or of a global measurement compared with a local measurement. And I think Indranil is going to discuss the Hubble tension in more detail, so I won't go into this, and instead focus on another global versus local measurement issue, or a set of these types of issues. So something that you saw here is that the error bars became smaller and smaller, right? So the Cepheids measurements are compilations of supernovae and of Cepheids that have grown historically over time, right? So we have made more and more measurements, which has led to larger and larger catalogs. And the CMB measurements itself, of course, have become much more precise with WMAP and Planck. So this is something that is new, and it's funny to see that about in about 1950, there's a conversation between Salam and Sharma where they discuss cosmology, and Dennis Sharma says that there's a new deal in astrophysics, which is that that now one can perform measurements of galaxies much further away, and so probe the cosmos at much greater distances, because we have measurements of radio galaxies as opposed to just optical galaxies. So in the last 10 or so years, and now with the onset of greater galaxy surveys, we again have such a new deal in astrophysics or in cosmology. So we can perform many more precise tests just because more data has emerged. So the local measurement that I want to discuss, of course, has to start locally. So this is a comparison of the local density field on the left-hand side, and a reconstruction of the corresponding velocity field on the right-hand side. That is centered on us. I hope you can see the small x in the middle. That says sort of what is the radial velocity field in our local environment. And something you can see is that, of course, the accumulation of matter that forms Shapley and Coma and Norma and all of these superclusters leads to a infall of velocities, both, in between us and Norma towards Norma, for example, and on the other side of Norma towards Norma as well, which leads to these red and blue, or the positive and negative radial velocities. And something else that you see here is that there seems to be a residual velocity field at larger distances. So the survey area only goes out to about 200 H inverse megaparsec. But even beyond that, at the top left corner and the right, in the bottom right corner, you see that there still is a bit of color. So we still have a radial velocity field there, and that is a residual velocity field of about like 150, 170 kilometers per second that these reconstructions predict, or infer, I should say. So this is something that in fact can be sort of put in context. So the very local dynamics, of course, start with our Earth going around the sun, and the sun going around the Milky Way, and our Milky Way falling towards Andromeda. So we have all sorts of local motions that are due to the local inhomogeneities. But the further out we go, the less motion we expect. And we do that because we assume that on some scale the universe will not have any imbalance in matter anymore. And so the distribution of galaxies is assumed to be statistically homogeneous on large scales. So this is something that one can quantify. And so the perturbations that we know to exist in the matter field based on the CMB of observations based on the ΛCDM model predict how this residual so-called bulk flow should look like on larger and larger scales. And this is what I show on the left-hand side. So you can compute this. This shows that at around 10 megaparsec, we would expect a bulk flow of about 400 kilometers per second for any observer anywhere in the universe, with some uncertainties, of course. But at about 200 megaparsec, that bulk flow should only be around 100 kilometers per second, and then decaying thereafter. So that, of course, proposes a test one could perform, which is to check whether these bulk flows actually agree with this sort of statistical expectation of ΛCDM. I see that there's some questions in the chat, but my cursor has disappeared. So if there's a question, just speak up, and I'll be happy to engage. Okay, so these tests have indeed been performed for a while now. What you see here on the left-hand side is just what was previously gray in my previous figure, that is now blue. And scattered around it, all sorts of measurements at different effective distances with different galaxy catalogs. You need a galaxy catalog for which you have distances to the sources and you have redshifts. So, there are not so many galaxy catalogs that actually have that out to great distances. Well, what you see is that pretty much all of them sort of agree with the ΛCDM expectation, which means that we, as observers of the universe, appear to be a typical observer. So it appears that maybe the Watkins 09 result at 100 megaparsec is a bit above, but the rest is all in agreement. Recently, there was another one by the Cosmic Flows 4 survey that claimed a measurement of 400 kilometers per second at 250 megaparsec, and that is clearly off limits, and so therefore it does actually pose the question of whether we live in a universe in which these bulk flows agree with the ΛCDM expectation. I see a raised hand by Arfan. Do you want to?
Basically this velocity measurement. So these are based on what signal we use to infer those velocity measurement. Is it optical, or is it some electromagnetic signal or something else?
So this is based on measurements like these. So we measure the light from galaxies. Most of these catalogs are indeed optical. So we measure the light from these galaxies. We measure their spectra. We measure their redshifts and the distances, and we have different methods for these things. And then we reconstruct either the density field, as we have on the left, and or, depending on the method, the velocity field. So it is really just basically, making measurements of certain galaxies and then compiling those in a big catalog. Is that sort of what you meant, or?
Yeah, thank you.
Okay. Okay, so this Watkins et al. Measurement was repeated recently by Whitford, which used about 40,000 galaxies of the same catalog, and they find that indeed there is a discrepancy, even though they disagree a bit on the strength of that discrepancy because of the estimators that they used in comparison with Watkins. But okay, so this might be an issue. More data would be great, but this is what we have so far. So of course, then that poses the question, if there is such a bulk flow, why is that? Is this something that's pulling us? And this is something that had been proposed already a while ago by Feint et al. that calculated, if there was one big mass that was at a certain distance, at which distance would that have to be, and how heavy would that mass have to be in order to explain the larger than expected bulk flow. And they estimated a mass of 10 to the 17 solar masses at a redshift of almost 0.01, at almost 0.1, which is of course extremely large and should not appear randomly within the perturbations that we have constrained the lambda CDM model to have because of the CMB perturbations. So however you phrase it, too large bulk flow or too heavy mass that is inferred, this is a potential problem for lambda CDM. So going now to a bit higher redshift, and I should maybe hurry up a bit, going out to a bit higher redshift, there was another measurement conducted recently by Konstantinos Mikas and collaborators that looked at scaling relations of X-ray clusters. And these scaling relations of X-ray clusters come in different combinations. So for example, the LX versus TX relationship is one that says over a great range of temperatures of these galaxy clusters, you find a power law relationship with the luminosity of those same galaxy clusters. And it turns out that the luminosity is of course cosmology dependent. So if you took these measurements, you could infer deviations from the Hubble flow. And what Konstantinos Mikas did is he investigated these relations in different directions of the sky. So basically he looked at direction-dependent deviations from the Hubble flow. And so what he finds is, what is shown on the right-hand side, is that there is sort of an imbalance in the scaling relation in different directions of the sky that could be interpreted as a direction dependence of the Hubble parameter, which in this case is about a 10% variation, which is of course massive. So this is already at higher redshifts than the bulk flow measurements, and it might be a completely separate observation, but it is of course intriguing that these bulk flows seem to persist. So why is it that we want these things to not appear anisotropic and not appear too fast at higher redshifts? It is because, of course, we assumed as part of the ingredients of our lambda CM model something that is referred to as the cosmological principle, that is baked into the choice of metric that we use. So the cosmological principle, which basically says that the distribution of light and matter is statistically isotropic around any point, is supported by looking at the CMB, and the CMB is, of course, the map you see on the left with fluctuations that are only 1 part in the 5, very small. And there is a caveat to make about this definition of the cosmological principle that I highlighted in red on the right-hand side, is that there are local departures from this isotropy and homogeneity, which of course those that I've referred to before. And these local departures make us, as observers of the universe, of course, move as well, just like anything else. And this indeed leads to one additional anisotropy in the CMB that is much larger than the others. So this is a 10 to the minus 3 anisotropy in the CMB that we see as the CMB dipole. The only multiple that is so pronounced, which we interpret as due to our peculiar velocity with respect to the CMB photons. So basically, the dipole is produced as the Doppler effect acting on the CMB monopole. So our velocity with respect to the CMB is interpreted as 369 kilometers per second. So this proposes a consistency check. If we have a velocity that we measure with respect to the CMB, can we measure the same velocity with respect to other high redshift reference frames? And while we do move with respect to the local group, and our local group moves sort of in this bulk flow, we expect that our movement with respect to the CMB should be exactly the same as our movement with respect to very high redshift galaxies. So this is a test that was proposed by Alice and Baldwin some 40 years ago, and goes as the following. So you assume an isotropic sample of galaxies on the sky. You assume that they have certain properties. In this case, we're going to consider them to have power law spectra, and we're going to consider their integral source counts to also work as a parallel. So basically I went from the right to the left in this figure. And an observer boosted with respect to this reference frame of sources would observe different effects. So I'm going to flip back and forth a few times here. I hope that it renders fast enough for you. The sources are going to be aberrated, so their angular positions are going to be changed due to special relativistic aberration. Their fluxes are going to be increased, and because their fluxes are going to be increased, their integral source counts in a given bin of flux is going to change as well. And all of these together lead to the appearance of a dipole that you can sort of see hinted at in the aberration of the sources. You see more sources on one half of the sky than the others because of your motion, and the amplitude of this dipole will depend on these properties. So in this case, the amplitude of the dipole, as I show in the bottom line, should be 2 plus x times 1 plus alpha, and the entire thing times beta, which is the boost. And this is a measurement that seems so simple that it had to be done, and so using measurements of the NVSS, a sample of radio galaxies, this could be attempted. And so what you need to do is you need to say, well, in the CMB, we have a CMB dipole that is so and so large that predicts beta to be 1.23 times 10 to the minus 3, which is these 369 kilometers per second. And plugging in the other observed values of your galaxy sample, we predict a dipole of 4.6 times 10 to the minus 3 in the CMB, in the distribution of NVSS galaxies. And so this is what Blake and Wall did in 2002, and they say that they have measurement that is consistent with the measurement expected from the CMB, and in fact they do find it consistent, but only because they have large errors, and in fact what they measure is 1.1 times 10 to the minus 2, which is twice as large, more than twice as large. And this is something that has been repeated since with other catalogs, and it has been repeated since with the same result. All of these dipoles that have been found in high redshift catalogs, those the NVSS or other radio catalogs, and also more recently, as I'll go into briefly, with mid-infrared measurements, report dipole amplitudes that are too large, that could be interpreted as a velocity with respect to the galaxy catalog that is much larger, or could be interpreted as due to a large-scale inhomogeneity, either of which would break this assumption that there should be large-scale homogeneity in agreement with the cosmological principle. So I'm just going to flash this briefly because this is what you can ask me about all day if you want. This is a measurement that we performed with a quasar sample that we collected from WISE that is sort of perpendicular in every possible way to the measurements with radio catalogs. First of all, WISE is a satellite. Radio observations have been done from ground. We have different types of influences on these sources. They're different sources entirely. All sorts of different properties make this sample completely independent. And we find a dipole in this sample of galaxies that are high redshift as well, and we find this dipole also to be about twice as large as it should be. So here you see some simulations that we ran. The CMB value, the one that you would have expected, is on the left, and the one that we found is on the far right. So in combination with the radio experiments, one can compute the significance of this departure, which is we should compute to be 5.1 sigma, which is indeed a tension with the assumptions of the ΛCDM model. And it is in fact at the same level as the Hubble tension, as people's notes recently. I'm not sure if it's as well established because it's not as well known, but at least the significance is the same. That also has been repeated by other measurements recently, which you can ask me about if you want to. So, for example, Damodal use the same sample, do a slightly different analysis because they plug it into a Bayesian framework, and they find 5.7 sigma significance. It has been done with a more recent Quaya sample as well. It's unfortunately not large enough to make a significant statement, but there's progress. So just to summarize, the presented selection of challenges, they are local measurements of peculiar velocities that indicate bulk flows extending out, extending beyond 200 megaparsec over H. These are things that I think are highly interesting because, exactly this contrast between local and global measurements is what might well help us understand where, if we need a new model. Then what I just presented is that measurements of distant radio and infrared sources show this overdensity number counts as well, as would be expected due to a peculiar motion of an observer, but it is too large to be in agreement with what is expected from the CMB. So that as well is in contrast with the assumptions made for ΛCDM. And so then we need to find solutions eventually, but this is something I'm not discussing here because it's only observations. These global anisotropies could of course be described by alternative metrics or non-standard perturbations that are otherwise not included in ΛCDM. But of course there are constraints of them because ΛCDM does actually constrain quite a lot. It is actually quite provoking to say that maybe the cosmological principle is not upheld because so many surveys assume the cosmological principle to hold already and assume large-scale isotropy and homogeneity to hold. So all of these observations suggest that one could analyze the data in a less model-dependent way, which we will be able to do with the upcoming data. So important here is that when we do consistency tests, they have to be constructed consistently, obviously. So we have to compare the theory with the observation in a way that we actually observe what the theory predicted and not something slightly skewed. So this was a discussion we had in the context of the matter dipole, but of course that holds everywhere, right? You need to compare apples with apples. So the more stringent tests become, the more accurate the theory has to become as well. And any type of circular reason should also be avoided. This is more general than in the cosmological principle case, but just speaking about how to analyze our observations in a hopefully model-independent way, which is hard because some data has been processed in a way that already built in model assumptions. This is not a statement at all that all data is like that. But I'm saying if it's been processed, that processing may contain model-dependent assumptions, and even in the theory, one may be tied to the ΛCDM model just a bit too much. So theoretical computations that avoid such model dependence are highly valuable, I think. So eventually we need a model that does better, but I don't have it. So I'll stop here. Thank you.
Okay, thank you, Sebastian, for the wonderful talk. Now we have 15 minutes for discussion. Any questions?
Yeah, this is Eric Lerner. I just have a comment. Cosmological principle is a necessary ingredient not only for ΛCDM, but for the entire Big Bang expanding universe model, of which ΛCDM is a sort of subcategory. If you don't have homogeneity, you don't get a prediction of an expanding or contracting universe. And it's important to point out that the cosmological principle was not derived or introduced according to the scientific method. Scientific method, as we all know, you make hypotheses based on observed phenomena, and then you test it against predictions. But at no point in the history of astronomy have we ever observed a universe that looks homogeneous at the scale that we can observe it. The cosmological principle was introduced for a non-scientific reason, which had philosophical reasons, that Einstein, aesthetic reasons that the universe should be this way.
Please,
And second of all, that it made general relativity equations easier to solve. So,
But it's okay.
We can look at this as a test of the validity of the cosmological principle, and it seems that it's flunked the test.
So I agree with that the cosmological principle was introduced not based on the scientific method as such. There were no observations to date that would have supported the cosmological principle. Right? It was introduced in 1933 by Milne, or at least formalized by him as such. It has been tested since to the degree that we can. The measurement I showed you is one measurement where it fails this test. There are other measurements where cosmic homogeneity is tested, where it seems to pass that test, or at least it is consistent with what it would predict. So it's a bit of a mixed bag of observations that we have, right? It's an interesting bag at the very least. When you say that the Big Bang model would fail if the cosmological principle wasn't such, I think that is probably a statement that depends on how large this violation of the cosmological principle is. Certainly, for example, if you had a universe that expanded differently in different directions, then nucleosynthesis would happen very differently or not at all like we expect. So I agree with that there's an influence that the cosmological principle ensures that things like nucleosynthesis work as we have learned them. But that isn't to say that there wouldn't be another solution that could make it work as well, giving up the cosmological principle. But thanks.
Okay. Other questions, please? Pavel, Kroupa? Pavel?
Yeah, hello. So, yeah, thanks. Since nobody's asking, I just wanted to say this was a very nice presentation. Thank you so much. And what is your take then? I mean, you've been working on this topic now for some time, right? And you've been seeing the evidence. You mentioned some of it. It doesn't look like it's going in the right direction for ΛCDM, does it? I mean, don't know what you think. Are you still ready to defend this theory for given the observational constraint we now have?
Luckily, I'm not asked to defend the theory. I'm going to defend the measurements that I made because I think that they do point at something where we can learn. So something I won't give up is saying that the ΛCDM model does exquisitely well describe the observations that we have made in the way that we've made them. For example, to bring up a new idea, the BAO measurements that I showed, they're done assuming that this two-point correlation function is going to be the same in any direction of the sky. With DAISY, we now have enough measurements that are at least sufficiently well distributed over the sky that one could perform BAO measurements that are anisotropic. Or that wouldn't assume isotropy. And when we speak about the Hubble constant, because it's tied to the scale factor, which is tied to the Friedmann metric, inherently assumes that this expansion is isotropic, which it may not be, as these results by Mikas may suggest. And indeed, recent measurements of anisotropies in the Hubble expansion have tested this. Right? Because maybe what we just said is that the cosmological principle is based on sort of just a set of assumptions, or it is a set of assumptions, as opposed to being based on observations or having to learn from observations. I'm willing to give up the cosmological principle if we need to. But it's hard to give it up because we don't have anything else in hand, right? So if I had a metric that would do everything better than lambda CDM, then I'd be happy to go forward with that instead. But it's sort of a tricky situation. It's a nice situation, but it's also sort of a tricky situation we're in right now, where some observations point at issues, and whether those issues can be resolved in lambda CDM is very unlikely. Sort of my personal take.
Yes. I just wonder what you sort of were alluding to it. There's another question, so I don't want to take much more time now, but the situation that we have this model and it being completely falsified by data, say. So, you mentioned some of these issues. I'm convinced it's completely falsified. But then the question is, what does one do with that? And I agree. I mean, one needs an alternative to continue working. We can do observations, get more constraints on a next model, which then has to be constructed by the community, right? And that is not quite on the horizon at the moment, it seems, right? That's what you're basically saying. So you're sort of stuck yourself in this particular framework, right?
Yeah, so maybe on the slide that I'm showing right now, I showed the references in the bottom line, or the second to last line, are references that I find interesting in exactly that context. We don't have a better model. We know that if we need a model, and of course we hold on to general relativity, we need some sort of metric, or at least some metric space in which to work. And so that's where these references that I list, Asta Heinessen and Tim Clifton and collaborators, have worked on sort of model independent ways of performing measurements from local observations. So we're sort of, it's sort of a cosmographic approach. We take local observations and we try to build up the rest from it, as opposed to assuming that on large scales we have, everything described by Friedman, Lemaitre, Robertson, Walker, and then sort of projecting onto the local environment from that. I think that's a valuable direction to go, but there may be others, of course.
Okay. Next question, Antonaldo.
Hey, well, thank you very much again for your talk. I have a very simple question. You properly mentioned the issue of circular reasoning that is often overlooked by many scientists in the field, I would say. So my question is very specific. How much circularity reason you think is there in the estimate of H0 with the CMB data? So how much can actually be due to a circular reasoning in the issue of the Hubble tension, right? Because it's not really independent in a way. So I don't know. I would like to have your opinion on this point. Thanks.
Yeah, of course. So I should say, I've not written a paper on the Hubble tension, so I'm definitely not an expert in that field. I've looked at some of the data, but it's sort of an outsider perspective that I could give at most. So circular reasoning in analyzing the data is, if I measure the Hubble constant, I can say what it is in a certain measurement, but the Hubble constant itself only makes sense in a Friedman, Lemaitre, Robertson, Walker context, right? If I had a universe that expanded differently in two different directions, I would have two Hubble constants, right? So that measurement is valid as such, but it is not necessarily something that confirms lambda CDM or whichever model predicted the Hubble constant. It is just consistent with, right? So in that framework, the measurement of the Hubble constant may well just be what it is. That's just fine. The model assumptions that may be in the data are to do with extremely difficult effects that need to be modeled with with more and more sophisticated data sets. So in these data sets, we have all sorts of selection effects that we need to model, and mostly for this modeling, we use simulations, and those simulations have to be built on certain assumptions. So it may be that by basing the learned selection on simulations that are based on assumptions, you introduce model dependencies that influence your measurement, or you introduce model dependencies that actually don't really influence your measurement, and you're just fine. I mean, I say this because I observed it, but I cannot make a statement as to how severe this would be. That would have to be tested, which of course only would be possible if one had an alternative model.
Thank you.
So the next question from Eric Leonard.
Yeah, I would disagree that alternative models and alternative metrics have not been put forward. I mean, really, since the work of Hannes Alfvén in the 1960s, the alternative has been put forward that the universe is not expanding, and the metric of the universe is this same Euclidean space that we have locally. And on the basis of a Euclidean non-expanding space, using existing known laws of electromagnetism and gravitation, Alfvén and myself and others have published as early as the 1980s predictions of a fractal distribution of, or approximately fractal distribution of matter, which really have been confirmed. That is, that the density of matter decreases with increasing scale on which you measure density. And in with such a fractal distribution of matter, then you don't conversely get any prediction, given general relativity, of expansion or contraction, certainly not on the scale of the Hubble time. So, if we use the criterion of comparing predictions with observations made subsequently, the cosmological principle is invalidated, and the Euclidean non-expanding metric is validated by this particular data set, which is on the inhomogeneous, roughly fractal distribution of
Please
matter.
the question, please.
Yeah.
It's a comment.
Yeah. The fractal distribution
I
of
invite
matter.
your comment on my comment. That's my question.
The fractal distribution indeed is observed at sort of smaller distances, right? This is something that those tests of homogeneity, I may actually have one of these on a slide here. No, it doesn't show. Can you see the slide here that says cosmic homogeneity? I'm assuming you can see it.
Yes.
Yes, we can see.
So this measures exactly the fractal dimension of sources in a given catalog, and you see it changes at small redshift to then at small distances to then match, presumably align at higher distances after around 200 megaparsec. So I agree that the fractal universe actually does describe the universe at shorter distances. At larger distances, it does appear to describe a homogeneous distribution better. But who knows what happens after this? I mean, this is a measurement using BOSS data, so it goes out to 1 gigaparsec, which is indeed quite large. Other measurements go out to a couple hundred megaparsec, and they already match this fractal dimension at 3. I'm not saying that there are no other models that were proposed. So if you proposed some model that seems to work in some range of the space of data, that I don't know it, but I don't disagree with its existence. But I suppose maybe what I meant by saying we need an alternative is we need an alternative that is competitive with ΛCDM as a whole, which for any given model would require as much work as went into lambda CDM, right? You need to work out all the perturbations and all the radiative transfer and all of it. But I don't know. I'm optimistic.
I would just say briefly that invalidating a theory does not require in science a alternative theory. A theory can be proven wrong without having the right answer.
That's right. Unfortunately, if your goal was to actually just prove wrong and discard lambda CDM, you would have to still agree that it's sort of a functional theory. Right? It's one that, for pragmatically, it just sort of works on much of the data space. Because in that sense, all theories are wrong.
Okay, we are running short of time. Thank you, Sebastian, for the wonderful talk. So let's move on to the contributor talks today. The first is by Pavel Kroupa. He's from Bonn University. The speaker has 10 minutes to presentation and 5 minutes for discussion.
Yes, I'll do my best. I'll do my best to keep the time. So this is a sort of antithesis to the talk we just heard, in the sense of arguing that the model has very, very serious problems. So let me just begin. So there are two fundamental assumptions which I would state, and that is that we do assume the Einsteinian-Newtonian formulation of gravity is valid everywhere, and that all matter is created in the Big Bang. That's a fairly important assumption. And then one does calculations in this framework, compares to observations like CMB galaxy rotation curves, and finds that one has to introduce, in addition, inflation, dark matter, and dark energy, in addition to these two assumptions. Right? So that's then sort of the lambda CDM model, and there are issues with it. So people have been thinking about cold, warm, fuzzy, axion dark matter. But for the one has to identify tests which are independent of the particular, very specific type of dark matter particle. The important thing here is that dark matter is indeed the core pillar of the model. So without dark matter, the whole thing really collapses. And so that's what one can test for. Now, there's been a lot of searching for dark matter. Nothing has been found since 40 years. This doesn't mean that it doesn't exist. It could exist, it just cannot be found in the laboratory. But then there is actually a particular way to test for the existence of dark matter, and that is through Chandrasekhar dynamical friction. And the case of the imaginary clouds are particularly relevant here. So the imaginary clouds are the two galaxies, which are fairly substantial galaxies. They are not very dwarfish. So this is, the SMC is 10% of the mass of the LMC, which is itself about 10% of the mass of the Milky Way. So we see here the Milky Way. Then we have the large and small imaginary clouds, which are clearly in interaction, leaving this imaginary extreme behind them with the leading tail and the trailing tail. They're moving past us near Perigalacticon at the moment. And the LMC-SMC distance is about 20 kiloparsecs here. In 3 dimensions, and Milky Way LMC about 60 kiloparsecs, and Milky Way SMC, LMC is 50, and SMC, there should be S, 60 kiloparsecs. So they are all very well immersed in their mutual dark matter halos according to the lambda CDM theory. That's what we are testing here. And so we have now exquisite 6-dimensional phase space Gaia data for this triple system. And we know their positions and velocity vectors, and therefore we can calculate the orbits into the past to see if there are standard model of cosmology compatible solutions. Okay, so here we have the dark matter halo of the Milky Way, the dark matter halo of, say, the satellite galaxy LMC or SMC. It's moving with a velocity, and from textbooks, we know that the deceleration suffered by this galaxy, because it's moving through the dark matter halo of this galaxy, can be expressed in this equation. This is Chandrasekhar's dynamical friction formulation. And we see that this depends, so the deceleration of this velocity vector here depends on the mass density of the dark matter halo, and not on the number density, and also not on the individual masses of the dark matter halo. It's the mass density, and that is fixed by the theory, by the CMB, Standard Model of Cosmology, fits to the CMB, and so this is not a parameter. There's no parameter we can vary here. There's just certain assumptions which went into deriving this equation, but one can check on them by doing actually live simulation. So we can take a live halo in a computer and model this actually through a galaxy falling in, and compare the rate of decay of the orbit with this equation, and it turns out to be pretty good, actually, remarkably, and there's been a lot of literature on that. So dynamic friction is very well understood, and we've now tested for the existence of dark matter based on this triple system using these position and velocity information we have today. And it's remarkable to realize when one does these calculations that the frictional deceleration of the large and small magnetic orbital motion due to Chandrasekhar dynamical friction is comparable to the gravitational attraction between the two. So this is now here the force as a function of the relative velocity of the LMC with respect to the SMC, and the dynamical friction of the SMC in the LMC dark matter halo, and the dynamical friction of the LMC in the small magnetic clouds dark matter halo are given by these curves. So this curve, they are velocity dependent because the dynamical friction depends on the velocity, while the mutual acceleration, which is the gravitational one, is independent of velocity. And so you can see that at the current distance of the two galaxies, the deceleration is actually comparable to the actual gravitational acceleration between the two, and this leads to a massive orbital decay. And so we now look at this remarkable publication by Massana et al., who've recently, this is in 2022, studied the synchronized star formation history of the large and small magnetic clouds. So this is the small magnetic cloud, that's the star formation rate density. This is the star formation rate density as a function of time for the LMC and SMC. And they discovered that they are synchronized. So up until about 3 billion years ago, which is here, there were 5 close encounters, 1, 2, 3, 4, and 5 currently. And when basically it means that when the LMC and SMC were in their mutual perigalacticon, the star formation rates of both galaxies went up, but that's very easy to understand and is seen in simulations, because the interstellar media of the galaxies are compressed through the additional gravitational potential when they are close together, and this boosts the star formation because more massive molecular clouds form and simply more stars form. And this is very beautifully seen in the star formation history of these two galaxies, and that kills lambda CDM because there are no solutions to the orbital solution. So we have here the pairwise distance versus look-back time. This is the large magnetic clouds, small magnetic clouds, as they fall through the galaxy, now actually simulated, including the Milky Way dark matter halo. And you can see here the time scale. The only possible solution is the one where they have one encounter, and so 2 encounters, but the first one here is just outside the 4 billion year window, and it's completely impossible to get them onto an orbit, which is so short period that they manage to have a perigalacticon in these times, which we have from the star formation histories. And so it is entirely impossible to get an orbital solution, and the solution is therefore not possible. And so there's no dark matter halos, and therefore this one test alone, there are many others, conclusively and absolutely and finally rules out the existence of dark matter. Dark matter simply doesn't exist based on this type of test. Now there are many other tests, and each of these tests is published. So today that this Standard Model of Cosmology remains valid. It remains valid with a probability of less than 10 to the minus 130. So this is the most falsified but believed to be true model ever. in history, and I think this is the greatest crisis in physics ever. And so now to the CMB issue, because if this model is ruled out, and I'm nearly finished, which initial conditions to use in cosmological simulations? So currently it is thought that the fluctuations in temperature of the CMB are the initial conditions at redshift of 1100 that any cosmological model must fulfill. So we have the model, the CMB, then a model of linear structure formation. This gives us the density fluctuations at, say, a redshift of 200. That's put into a code, which then calculates the nonlinear structure formation to compare with the current observed universe. And so the CMB power spectrum has been discussed already. It's an extremely well fit by the standard model of cosmology with dark matter, and here's a Mond cosmological model without cold dark matter. Fits nearly equally well, this power spectrum, but there is an issue even with this, and that is as follows, and I'll refer to the talk by Nick Samaras. There's two problems. The CMB has more power and higher temperature on the southern hemisphere, and remarkably, there is a much more than 5 sigma larger number of early type galaxies on the southern hemisphere than on the northern hemisphere. Are these connected? It seems to. And there's a paper discussing this, here's the distribution of galaxies, and the southern hemisphere has significantly more early type galaxies than the northern hemisphere, so that's just one thing telling us that there's an anisotropy on large scales. And here's now the final message. If we start with the CMB at the redshift of 1100, which has no fluctuations, then the photons propagate through the universe. They are deflected through weak lensing as the structures evolve. Their energy changes through scatterings on the electrons. The energy changes through evolving potential wells, and sources appear. So today we see a CMB as a consequence of all these effects. And that means that if we want the fluctuations at that time here, we need to correct for all of these. Now, that's of course known. However, obviously, all of these corrections are dependent on the cosmological model designed. How quick and how large are the potential wells which develop, how much matter is in these potential wells, how many electrons, and so on. And so it means that the initial conditions at redshift of 1100 must be recalculated for every cosmological model separately, and given the CMB observed today, every cosmological model has its own unique CMB power spectrum at this redshift. So the lambda CDM power spectrum today is not the correct initial condition for any other cosmological model. And with that, I would like to end. Each cosmological model needs its own fluctuations in the CMB. The currently published CMB power spectrum is only valid for the lambda CDM model, which, however, is entirely ruled out by the observational data. Thank you.
Thank you, Pavel. You have 5 minutes for questions.
Hello.
Hello.
Yeah, I have one question.
Yes, please.
Hello.
Yeah.
Yeah, but isn't it that the lambda CDM model satisfies like almost all the current scenarios, like including dark matter and the rotation curves that factor in other models? So, like, do we again need to recalculate those models? Like, do we need to again put those models back in check? Because then we will need alternate theories for dark matter to satisfy the structure formations also.
Well, yes. So I think I understood you at the beginning that you said that the dark matter models accounts for the rotation curves, right? I think you said that, right? But that is actually not correct. So there are papers, very nice papers by Stacy McGough, who's been looking at the shapes of the rotation curves of actual real observed galaxies, and they are not matched by the theoretical galaxies in the model in terms of the NFW dark matter halos coming out of the simulation. So one cannot match the rotation curves by dark matter halos. Nearly everybody makes the mistake that you think that one thinks I have an observed rotation curve and I can fit a dark matter halo to that. That's just wrong. You can't. You can do it, but that has zero value whatsoever, because what you have to do is you have to take the dark matter halos from the cosmological structure formation simulation, they essentially give NFW type halos, and those do not fit the rotation curves. And yes, so one has to then re-evaluate everything in terms of a different theory, but as we've just heard from just now, from the talk and the discussion, there is currently no real good alternative to do this whole body of work in a different cosmological framework, and that is certainly a certain problem which we are facing. However, this just means that the community has to sit down and develop a new model, right? That's sort of the obvious thing to do. And by keeping oneself locked up in the lambda CDM framework, that will not happen. And that seems to be currently the case, that the whole community is locked up in the lambda CDM framework, which is radically ruled out by the data. Without dark matter, there is no lambda CDM model. And therefore, there's a serious problem with the community currently.
Okay, thank you. Any other questions?
Can I share my screen?
Hi, Lior. Nice to see you.
Good to see you.
Yes.
You can. I have to stop sharing. Yes.
Yeah, greatly. Yeah. Okay, now I can turn. Let's see. Can you see my screen now?
Okay, Lior Shamir from Kansas State University, please.
Yeah, thank you. So I'm going to make 3 points. So the first point is that the Redshift model that we use has a small bias. It's not a substantial bias. It's a very small bias, but it's pretty consistent. And the second point is that the bias tends to increase as the redshift gets higher. And that is an important point because that can explain all those galaxies that are older than the universe, and the black holes that are older than the universe, and the stars that are older than the universe, and the HO tension, and all these wonderful things that now we struggle to explain. And the third point is that it's very consistent across different telescopes and different data sets. And what I made, all the data is open. So everyone can access the data and make sure that everything is consistent, and also maybe expand on it, maybe see things that I missed in that data. But all of the data sets are open. It can be very easily, everything I say can very easily reproduce. So the trick is to use the rotational velocity of the Milky Way at 220 kilometers per second. It's not very high velocity, but it's a reliable velocity. It's something that we know, and we can use it as a baseline. So what we can do, we can look into galaxies that rotate, the redshift of galaxies that rotate in the same direction relative to the Milky Way, and galaxies that rotate in the opposite direction relative to the Milky Way. With one galaxy, obviously we cannot do that because we don't have ground truth for that, but with a population of galaxies we can. And that's what we can see. So that analysis of several different telescopes. So each experiment is independent. So these are independent experiments. So we go through the southern hemisphere, taking galaxies from around the southern galactic pole that's using a DESI legacy survey. And all of them show that galaxies that rotate in the same direction relative to the Milky Way has a slightly higher redshift than galaxies that rotate in the opposite direction relative to the Milky Way. So, and it's very consistent across different telescopes, different analysis method, and all of these experiments are based on fields around the galactic pole. So it's always that the galaxies that rotate in the opposite direction relative to the Milky Way have lower redshift. And that's data from HSC. So HSC goes a little bit deeper. So we can see, we can separate into different redshift ranges. And what we can see is that the bias increases when the redshift gets higher. So we see here, it's very consistent in both the southern galactic pole and the northern galactic pole. We see the pink and the green line. So both of them show exactly the same thing. And again, all the data are available in the URL there, but it's also in the paper, so you don't need to take any notes. It's also in the paper. You can find the URLs. And I also use some third-party data sets not prepared by me, and show exactly the same thing. It's completely identical. Whatever data you're using, you're going to see the same thing. And these data are also public. You can try those too. And here's why I think it will get even larger in the deeper universe. The bias will increase. So what we have here, that's a Webb deep field that was taken inside the Hubble UDF. So that makes it pretty close to the southern galactic pole. And when we look deep in the image, we see something very interesting. We see that almost all galaxies rotate in the same direction, which is also the direction opposite to the direction of rotation of the Milky Way. So, and how can that happen? So one explanation to that can be that galaxies that rotate in the opposite direction relative to the Milky Way, just because of the rotational velocity, they just seem brighter to a Milky Way-based observer looking at them. And that the difference is so high that it makes the population different. It's so obvious that we don't even need any like algorithms or data sets or things like that. A 5-year-old child looking at the image can immediately see that there's a difference here, that there's some sort of anomaly here. And that might seem surprising, not to say crazy, but not if we look at the data. Not if you look at the data. So that figure was published in 2022, in the paper that's specified below. What we have here, and at that time, obviously, that was before Webb started providing data, so I had no way to know what Webb would show. But that is based on 1.3 million galaxies from the DESI Legacy survey. And what we see, that's the distribution of the galaxies all over the sky, based on the difference between the number of galaxies that rotate in one direction compared to the galaxies that rotate in the opposite direction. And that is not a that's direct measurement. That's not a statistical model of any kind. It's direct measurement. With 1.3 million galaxies, that's enough galaxies to make direct measurement. And what we can say, for instance, is that where the ultra deep Hubble UDF is, we expect a higher number of galaxies that rotate in the opposite direction relative to the Milky Way. And just in the Webb deep field, we can see this exactly that. That's exactly what we see. But the magnitude of the difference is much higher than what we can see with the DESI Legacy survey. And so that's if the redshift is not biased, then what we have is an anomaly in the large-scale structure. We can tie to theories like rotating universe or black hole cosmology and so on. I, for some reason, tend to believe that it's a bias in the redshift. It's not an anomaly in the large-scale structure. It is an anomaly in the redshift that fits very well with many other observations, and it also fits with the data. So, well, I cannot be 100% sure of that. I mean, all bets are on, but that's what it seems at this point. And that's about it.
Okay, thank you, Lior, Shamir. Questions? Yeah, Pavel. Yes.
Yeah, thank you, Lior. And just a question: Have you compared what you expect from the standard cosmological model, which is still the standard in terms of comparing to data today? So, do you expect this type of correlation of spins of galaxies in that model?
Well, I don't think it's a feature of the large scale structure. I think it's a feature of the galaxy, some anomaly in the physics of galaxy rotation, and the light that we observe because of that. So in my opinion, it's not a feature of the large scale structure, but if we take it as an anomaly in the, not an anomaly, a bias in the redshift, then it fits perfectly to observation. It can explain fairly well why we see all those, let's say those early type, very high redshift galaxies that are also, that look old, that look mature, but still have very high redshift. So that can explain that. So, and several other, like the HO tension and things like that. So the HO tension is a problem with the, in standard cosmology. That can explain that HO tension in a fairly straightforward way.
So you're suggesting some sort of redshift effect in
I think
non-standard redshift effect, or
it looks, well, that's what the data shows, that the redshift is not exactly what we think it is. There's a small bias, but consistent bias. And the data shows that. And again, the data are open. Take a look. I mean, it's pretty easy to use the data. In a matter of like, I don't know, 20 minutes will take to just reproduce this thing, because it's organized in a way, in that way. But we can, now we have all the problem of standard cosmology, like those galaxies that seem to be older than the universe, or stars that are older than the universe, or the HO tension, and that explains all that. So if you connect that data with all the gaps that we have in standard cosmology, I mean, that can close these gaps. Yeah, it opens new questions, right? It introduces new questions. So how can the redshift be biased that way? What happens to the redshift? Why is the measurement different than what we thought? So it opens new questions, but it also answers many questions that we have right now that we can't answer at this point.
Okay. Next question by Louis Marmot.
Yeah, hi, Lior. That's an interesting observation you've made, and actually I've read your paper as well, and you make a link with tired light. What I don't quite understand is why galaxy rotation, why a galaxy rotation in the same direction as the Milky Way would bias it in one specific direction. Why wouldn't it be in the opposite direction, or like how is the bias produced by tired light? That's what I'm wondering. Well, if you have an idea.
No. Well, there are two separate things: the bias and the link to the tired light, which is a weak link. It's not a strong link. It's a weak link. Let's make it clear. It's a weak link. It's more like an assumption or an hypothesis to tie. But these are two separate observations that are made in one maybe in one or two papers. One is the difference in the redshift because of the rotational velocity, and that is aligned with you. The rotational velocity does add to the Doppler, but we ignore it because it's supposed to be negligible. So redshift model that we have, because 220 kilometers per second is really negligible compared to, I don't know, 30,000 kilometers per second. So it's really negligible. So we don't take it into account, assuming that it's negligible. But that is based on the assumption that we know everything about the physics of galaxy rotation, and that assumption is a little risky because we don't have proven physics that we fully understand the physics of galaxy rotation. It's a little, I mean, we can assume dark matter, you can say MOND, you can say other things, but we don't have a proven theory for that, and we do see the anomalies, and it's still challenging us. So that's one thing. The other thing, that the link to the tired light is because it increases when the bias increases when the redshift gets higher. So something happens, and the rotational velocity of the Milky Way is 220 kilometers per second either way, whether the galaxy is close or far. So what happens to the light on its way to Earth or something like that causes it to happen? Again, I don't know for sure if it's tired light. It's one of the possible explanation to that, but something happens with the distance. Something happens there with the distance.
Okay, thank you.
Okay, thank you, Leo, for the nice talk. So let's now move on to the next speaker, Martin Lopez Corridoira from the Institute of Astrophysics, the Canarias. He's talking on galaxies older than the universe at Z-8. Martin.
Hello, I'm going to share. Wait a moment. Let's see here the share. No.
Yeah.
Now. Hello, everybody. I'm going to talk about this topic of the galaxies, maybe older than the universe, or maybe not. This is the question. Some of the tensions of the problems of the ΛCDM are related with galaxies at high redshift. We have many observations that present some problems, like the high abundance of metals, the metallicity, high abundance of dust, calcium-2 absorbers, also coal gas, polycyclic aromatic hydrocarbons, for instance, that they should take a long time to be created, at least 1 gigayear, and they are already observed at a redshift 7, for instance. The reionization is earlier than predicted. There are supermassive black holes at high redshift belonging to quasars, even 10 to 9 solar masses, which should not be there according to the standard scenario of galaxy formation and the standard cosmology. There are galaxies at redshift 14, confirmed spectroscopically, and more remarkably, there are very massive galaxies at redshift around 8, with already with presence of all stellar populations. All of these problems could find a solution if we admitted that the universe is older than it is predicted by the standard universe. Rather than 1 gigayear old for redshift 6 or 0.6 gigayears for redshift 8, which is a very short time for the creation of all these elements, if we had a much older universe, this will solve all these astrophysical problems. Although, of course, cosmologists will not agree to change the cosmological model. I'm going to focus in the last problem, in the existence of massive galaxies at redshift 8. This is already known, the problem, since almost 20 years ago. In words of Steinhardt, it is called the impossibly early galaxy problem, by which we find a density of very massive galaxies much higher than the predictions. The predictions are here in solid lines, and the points are the observations. There are 2 or 3 orders of magnitude much higher, especially at redshift like 8 or 10. When we talk here about massive galaxies, we are talking about galaxies with a mass of stellar mass around 10 up to 10 solar masses, 10 up to 10, 10 up to 11 solar masses, almost like the Milky Way or Andromeda. More recently, with the James Webb data, Lavey et al. Has claimed that there are galaxies like this at redshift 8, around redshift 8, when the universe was only around 600 megayears old. There are galaxies with stellar mass larger than 10 up to 10 solar masses. The spectroscopy, the redshift of these objects was photometrically, most of them, but later it was confirmed spectroscopically, and it is confirmed that they are really at redshift 8. It's not a problem of the redshift. Some of these galaxies, many of these galaxies present a strong Balmer break, which is indicative of a very old stellar population, or relatively old stellar population. Indeed, with our analysis by Steinhardt this year, they find that some of these galaxies, of this Lavey sample, have a Balmer break larger than expected if they were younger than the universe. So we see here some points. It's true that they have a big error mark, but we see some points only with the Balmer break that they look to be older than the age of the universe. It is, however, a fact that the Balmer break alone cannot be used to determine the age of the galaxy, because there is a degeneracy between the dust, extinction by dust that produces reddening, and the age. So we need to analyze the full spectral energy distribution. The Labé galaxies, these galaxies that are supposed to be very massive, were selected to have a double break in the spectral energy distribution. They have a Balmer break and they have a Lyman alpha break. And moreover, there is a lack of emission in the far ultraviolet emission. With all these characteristics, it is more easy to break the degeneracy because the presence of the Lyman alpha break indicates that there cannot be so much extinction. Otherwise, we could not see this Lyman alpha break because a large amount of dust will remove this feature. Labé and collaborators and other authors also try to fit this spectral energy distribution using populations younger than the universe. Of course, it is a taboo nowadays among most of cosmologists and most astrophysicists to use galaxies older than the universe. So in their analysis, they always use ages of the stellar population younger than the universe. In order to reproduce the big Balmer break, they use a very dusty stellar population, as we see here in the red line. So they can reproduce the Balmer break with this dust population, and they reproduce the Lyman alpha break with a different young stellar population. This, however, in my opinion, is not correct. Mathematically, you can fit the spectral energy distribution in many ways, but this has no sense because the young population should have at least as much dust as the old population. We cannot put a young population without dust and an old population with dust. Should be the opposite, or at least it should be the same amount of extinction associated to the stellar formation regions. Another possible solution proposed by Wang et al., for instance, is introducing an AGN, a quasar. We know the quasars should be blue rather than red, so they should not produce the solution in the Balmer break to be very red. But if we introduce an AGN with a very high amount of extinction, a heavily scored AGN, we could reproduce at least partially some part of the Balmer break that we see here. However, the problem is that the AGN should have also an important contribution in the far ultraviolet, even with extinction. What I have observed in this paper by Wang et al. Is that in order to remove the emission, the possible emission of the AGN in the far ultraviolet, they use an extinction curve which is very far from realistic. They use an extrapolation from Calcetti et al. Law multiplied by a power law function, so it is modified, and below 1,000 angstroms you have hundreds of times more extinction than invisible. This is unrealistic because we know from the precise measurements in the local universe that the extinction below 800 angstroms at rest is much lower than in the larger wavelengths. There is a hole of extinction below 800 angstroms. And this is not taken into account in this analysis because if we take this into account, you should have an important emission of AGNs. So in my opinion, there is a problem with these kinds of analysis too. I have carried out my own analysis taking into account the two circumstances that the young population should not have lower amount of dust than the old population, and also including an AGN with the proper extinction curve. When we include only two stellar populations, we see that the possibility that these galaxies are younger than 600 megayears, which is the age of the universe at Redshift 8, is excluded at 2.9 sigma. And if we reduce the age of this galaxy to 300 megayears, it will be excluded at 7 sigma. If we allow an AGN component, only when the extinction in the AGN is extremely high, we talk about extinction of more than 4 magnitudes invisible, then we will be roughly compatible with the age of the universe. We will get a possibility of 600 megayears within 1.6 sigma, which is roughly compatible. Although still 300 megayears is excluded at 4 sigma. The problem with high extinction AGNs, which is usually a hypothesis in this fashion topic nowadays, which is called the little red dots. The problem is that we should observe also another signs of AGN. We should observe variability, far ultraviolet. With variability, we should observe high emission in mid-infrared due to the high amounts of dust or millimetric wavelengths. We should observe a strong emission at X-ray, and also we should have a supermassive black holes because we need a lot of extinction and you increase the luminosity of the AGN. All these features have problems because observationally we don't find far ultraviolet variability, we don't find detection in ALMA, for instance, we don't find detection in X-ray. So there are a lot of problems with this hypothesis of highly extincted AGNs for these kinds of objects. Summing up, these objects are very peculiar. These little red dots are called at a redshift around 8. They have a double break in Lyman alpha break and Palmer break, and moreover a lack of emission in far ultraviolet, which allows to make a more or less accurate estimation of the age of the populations and the extinction in these objects, including AGNs and several stellar population components. There are two possibilities. Either we have some small but significant contribution of an AGN with a very high extinction, which is problematic in many senses, because this should present X-rays, should present variability, is problematic in many senses. And even so, you should have a population of the stars around the age of the universe. So this means that exactly in the moment in which the Big Bang was produced, the first stars were started to be produced. The other solution is that the AGN contribution is very small. There is some AGN contribution, but very small. But then the age of the stars should be still much larger. And then there is a serious tension with the age of the universe. I have to remind, however, that all these conclusions result from several approximations in stellar astrophysics. Yes, we are taking some models of stellar emission, including some IMF or whatever, and also some extinction. So this should be taken with a grain of salt, and we should do further research. This is not a definitive result. But it is promising to see that there are, apparently, the most likely solution is that these galaxies are 1 or 2 gigayears old at redshift 8, which is at least challenging. Thank you.
Thank you. Thank you, Martin. Now it is time for questions. Well, I have a question. How do you see a cosmological solution for this problem? Martin?
Well, at present, we have to be sure that the problem is definitive and there is not any problem in the measurements. Still, there are some uncertainties, at least it's a tension. And the cosmological solution is changing the cosmological model, of course. ΛCDM has a very clear prediction that at redshift 8, the age of the universe is 600 megayears. If we find that the galaxies, as I see here, are around 1-2 gigayears, and the probability to be younger than the universe is relatively low, if we corroborate this means that in some way the ΛCDM model is falsified. It's clearly like that, and we have to change to another cosmological model in which the age of the universe at redshift 8 is much larger. There are many alternatives, of course.
Thank you. Thank you. There is a question from Robert Monjo. Whether this problem can be solved with a more effective gravity such as MOND or others.
I have not seen any predictions of MOND, or if there is any MOND cosmology, a complete MOND cosmology with all the predictions of the age of the objects or age of the universe at a given redshift. I have not seen this. There are some other models, for instance, the model RH equals CT, the model by Fulvio Melià, in which they predict that the universe is at least 1 gigayear older. So it is a Friedman-Robertson-Walker metric. It's a general relativity, and they predict that the universe is much older at higher redshift. And there are other possible combinations. There are also combinations of standard cosmology and some component of non-cosmological redshift that they can change in some way the numbers. There are many possible solutions. About MOND, I don't know. I have not seen any publication in which they publish the prediction of the age of the universe as a function of redshift.
Okay, any questions further?
Hello?
Yeah, perhaps
Okay.
I could ask a question here, Rajan Gupta, that I have a model in which the coupling constants vary, and that gives the age of the universe to be 26.7 gigayears. And that I have seen that might be one of the model which allows the formation of the galaxies at time which is an order of magnitude higher than what is in the lambda CDM model. So that might resolve this problem which Martin has been discussing.
I agree. I know your model. Indeed, I cite your paper in this work, and this is one possible solution. Of course, if you have a universe which is 26 gigayears old nowadays, and at redshift 8 is also several gigayears, of course, this is a possible solution. Another thing is other problems that this model may have to make compatible with other information about, for instance, about the globular clusters in our galaxy, that we don't see many objects that are more than 20 gigayears old in the universe. So maybe there are some other kinds of problems. But for this particular observation, this would be a solution, of course.
Yes, Indranil has something to say. Ask the question, please.
Yes, I wanted to mention, like, so it seems to me the problem is that some of these stellar populations are themselves older than the predicted age of the universe at that redshift. So in that case, forming the galaxy faster, as MOND would provide, that alone will not solve the problem. Did I understand that right?
Well, the question is exactly that the stellar populations look older than the age of the universe at that time. About MOND, as I have repeated before, maybe you can inform me because you work more in that. I don't know. I have no numbers. I cannot compare with the prediction.
In MOND, the expansion history is the same. So MOND
doesn't give exactly. Then it is not any solution with MOND, in particular for high redshift objects. Yes.
Right. So, but the models that we're discussing in the chat, like with the linear expansion history, that obviously would give a lot more time. For example, at redshift 8. Because in lambda CDM, the idea is that at high redshift, the expansion history is going as t to the 2/3. So obviously, if it was linear, that would give 50% more time. So I suppose that would help the problem. But is that likely to be enough then? Because even if you make the expansion history linear instead of t to the 2/3, you'll only be able to gain a factor of 3/2 in the age. Is that likely to be sufficient?
Yes, it is. As I mentioned before, the model of RH equals CT, also called zero active mass, is the one that predicts a linear expansion.
Yeah.
And exactly, there are numbers that they give, particularly for redshift 8, they give an age of the universe 1.5 gigayears instead of 0.6. And this would be enough, yes.
Okay, one quick question from Pavel.
Thanks.
Pavel?
Yes, I'm here. So thanks, Martin. Great to see you again. And just a comment that if the IMF varies as we think it does, then it reduces the masses of the galaxies. I'm not sure if it changes the age estimates in terms of the red. Maybe some dusts would potentially help. You know more about that. But this reduction in mass, if the IMF was more top heavy, as we've also calculated and published, then that still is not enough to help lambda CDM. One does need, I think, an older universe.
I think so. In any case, I have checked with several IMF, and the problem is that we see very red objects, and very red objects can only be explained in two ways. Either you put dust or you put age. And this does not depend on the IMF. Of course, you can change slightly the numbers, but very slightly. It's a second order effect, not so important. Yes, I agree.
Okay, thank you, Martin, for the nice
You're welcome.
So we now move on to the next speaker, Ardra E.S. from Mahatma Gandhi University. She's talking on evolution of Hubble parameters from Pantheon Plus data and comparison with cosmic chronometers. Ardra.
Hi. Yes. Hi. I shall share my screen. Is it visible? Okay, my talk is on the evolution of Hubble parameter from Pantheon Plus data and comparison with cosmic chronometers. And here's the outline of the study. We estimated the Hubble parameter evolution for the ΛCDM model and the three special cases of beta cosmic model using the supernova data, the type 1 supernova data, that is the Pantheon Plus data. And we studied the behavior of scattered rays associated with the Hubble parameter values while moving to higher redshifts. And then we carried out a Bayesian model comparison between the ΛCDM model and the three different cases of eternal cosmic model using the cosmic chronometer data. And here are the data we used in this analysis. The first one is the type 1 supernova data, which is basically an apparent magnitude and redshift data. Here we used the most recent Pantheon Plus data containing 1,701 data points, which are collected from 1,550 different supernovae. And then the cosmic chronometer data, which is a compilation of 34 data points of Hubble parameter values from different works and are based on the observation of luminous red hot galaxies, which are commonly called the cosmic chronometers. And this evaluation of Hubble parameter. So, okay, so this evaluation of Hubble parameter. So this evaluation of Hubble parameter is from the works based on the observation of red hot luminous galaxies, red hot galaxies, which are commonly called the cosmic chronometers, and these are evaluated from the model independent approaches. And then the ΛCDM model, as you all know, the standard cosmological model. The model grants us an expression for the luminosity distance for the flat geometry cases, which is given in equation 1. And here, as we can see, the DL, the luminosity distance, is a function of redshift, the matter density parameter, and the cosmological constant density parameter, and those values are given there. And to evaluate the Hubble parameter values for each redshift, we found out the normalized probability distribution for each edge for 1,701 redshifts. And the normalized probability distribution is given as in equation 3. And the normalized probability distribution is a Gaussian type, which is peaked at a particular value of with h and has a definite spread. And this evaluation of Hubble parameter is model independent. And these are the Hubble parameter. This is the Hubble parameter evolution we estimated from the Pantheon Plus data for the eternal costing model, and the plot is Kyu-Hyun. And here the red line shows the theoretical prediction for Hubble parameter evolution in the ΛCDM model. And here we estimated the Hubble constant, which is the present value of Hubble parameter, using the Monte Carlo method, which turned out as 72.39 kilometer per second per megaparsec. And then the eternal costing model. The eternal costing model is a Big Bang cosmological model in which the scale factor A varies linearly with time. That is, A is equal to mct. Here M is a function of the curvature parameter K and the total density parameter omega. And the well-known RH equal to CT model is a special case of this eternal costing model, which is delimited to flat geometry case. And here also the model answers an expression for the luminosity distance in various geometries, which is given in equation 5. And here the function sine and takes different forms for different spatial geometries. And here are the Hubble parameter evolution we estimated for the 3 different cases of eternal costing model using the Pantheon Plus data. As you can see, the Hubble parameter evolution is given in 3 plots. We took the 3 special cases for eternal costing model based on the total density parameter values, the omega equal to 0, omega equal to 0, omega equal to 0, omega equal to 1, and omega equal to 2 cases. And the evolution for Hubble parameter in all these cases are given here. And the green lines correspond to the theoretical prediction of eternal costing model for the Hubble parameter evolution. And in all these 3 cases, we calculated the Hubble constant values, which are given here, which are all in the units of kilometer per second per megaparsec. And here's another result, the evolution of scatter associated with the Hubble parameter while increasing redshifts. And as you can see, the 2 plots which is depicted using Gaussian process regression method. And it's obvious that in two of these models, the scatter associated with the Hubble parameter increases with redshifts. And it clearly indicates as the indeterministic characteristic of Hubble parameter when moved to higher redshifts. And does it indicate any fluctuating stochastic evolution for the early universe? And next, the Bayesian model comparison. The posterior probability for a model, that is the probability for a model M1 to be tracked is some given data and some background information is given. As the posterior probability can be calculated using the Bayes theorem, which is given as in equation 6, and the Bayes factor for evaluating the Bayes factor, which is a ratio between the posterior probabilities between 2 models. The Bayes factor is a ratio between the posterior probabilities of 2 models, and here the probability that the data to be true is the normalization constant, which cancels out by taking fraction. And if we set that the prior probabilities for the model M1 and M2 is same, the Bayes factor B12 for model M1 and M2 is simply the ratio between the likelihoods. And for the evaluation of likelihood for a model M1, we again use the Bayes theorem as given in equation 8. And here, the likelihood for the model demands is an expression for the likelihood of the parameter theta of the model, and which is usually expressed as in the chi-square statistic. And here is the plot depicting the evolution of Hubble parameter in 4 models we consider, the ΛCDM model and the 3 different cases of eternal costing model. The evolution is plotted along with the cosmic chronometer. And here are the results from our Bayesian model comparison. And the 4 models are given here and the corresponding likelihoods. And about the Bayes factor, the Bayes factor B12 between model 1 and model to the lambda CDM model and the omega equal to 2 case of eta positive model. The base factor is huge, indicating that it's favoring the lambda CDM model. And among the 3 cases of eta positive model, this particular model where omega equal to 2 is most favored among eta positive models than the omega equal to 1, the RH equal to CT, and the omega equal to 0. That's in the type models. And we also carried out another Bayesian comparison study after excluding 4 data points from the cosmic chronometer data, which are from these papers. And we found that they are the outliers with very small error bars. They are outlying in the Hubble parameter evolution we estimated. And after excluding the data, 4 data points, we found that the likelihoods as is and the base factor, about the base factor, the B12, has decreased considerably, and there is a considerable change of decrease in the base factor B12, and this difference can indicate an incompatibility between the supernova data and the cosmic chronometer data. And here's a quick summary of what I have said today. And we estimated the Hubble parameter evolution from the lambda CDM model and the 3 cases of eta positive model using the Pantheon Plus data. We analyzed the scatter and found that the scatter associated with the Hubble parameter is increasing with redshifts. We carried out a Bayesian model comparison with the cosmic chronometer data, and there happened a huge base factor which is in favor of the lambda CDM model when compared to cosmic chronometer data. And from an exclusion of 4 data points from the CC data, we found that there's a huge decrease in the base factor but it's still favoring the lambda CDM model but there occurred a large decrease in the base factor, and this hints at an incompatibility between the supernova data and the cosmic chronometer data. And about the Bayesian model comparison done between eta positive models, the omega equal to 2 model is much favored than the other 2 models, the omega equal to 1, the RH equal to CT, and the omega equal to 0 models. Yeah, that's it. Thank you.
Okay, thank you, Arthur. Now it is time for questions or comments. Yes.
So I wanted to ask, with regards to the supernovae, like, are you using the Cepheid based calibration of the supernovae locally as like an additional constraint, or do you just treat the supernovae as like uncalibrated?
No, we use the Pantheon Plus data, which are not included these Cepheid stars.
So they are calibrated or not?
No.
They're not. So okay. So the supernovae treated as uncalibrated, standard candles. That means any information on the value of H0 is coming from the cosmic chronometers then.
About the H0 value from the cosmic chronometer then.
Yeah, okay. So one thing I was wondering, when you can you go back a slide to when you were saying there's like a inconsistency perhaps between the supernovae and the cosmic chronometer data?
Yes.
So do you know which redshifts this inconsistency is at, or in like what form the inconsistency takes?
I didn't get what you asked.
Because you had a slide just now where you were saying that there's an incompatibility with the SNE and CC, but have you constructed sort of H of Z graphs based on both of these and tried to show at which redshift the inconsistency is? So in what way are they inconsistent? I mean, other than just giving a high chi-squared or something, where exactly are the supernovae and cosmic chronometers inconsistent?
You may go to the
Yes.
Not one. One more.
Yeah, I see. So, okay, so the h of z curve here agrees, but that seems to agree fairly well with the observations. I'm not entirely sure how there's an inconsistency with supernovae. But
we are actually excluding the outliers, which are outlying those points which are outlying our Hubble parameter equation.
okay.
Yes.
No, it's just interesting that there's some tension between the expansion history sort of traced by cosmic chronometers and traced by supernovae. That's basically what you're saying. And that's like not dependent on the cosmological model as such, right? Okay.
Okay. Any other questions? Okay. Thank you, Albert. If there are no questions, let us move on to the poster session.
Thank you.
The poster session is 5 minutes for the speaker and 5 minutes for discussion. The posters are already in the website. So the poster note is by Eric J. Lerner from LPP Fusion. Eric, please.
Okay. Okay, well, I'll take a little bit more of that time for presentation, but let's just move along. So I'm talking about JWST observations invalidating the expanding universe hot bang hypothesis. So we're talking about the Tolman test, which was proposed almost a century ago. Tolman pointed out that in a Euclidean non-expanding universe, surface brightness is constant. So surface brightness is the apparent luminosity of an object divided by its apparent area on the sky. The expanding universe, any expanding universe prediction, is that the surface brightness declines sharply with redshift, 1 plus z cubed. One factor is from the stretching of time, and 2 additional factors are from the increase in angular diameter because of an optical illusion that the light was emitted when the object was closer. So these are very different predictions. What does JWST say? Well, we did a preliminary analysis concentrating on 69 galaxies with spectroscopic redshifts. Now, we were using a different measurement, so we calibrated our measurement technique against Morishita's, and we're going to be doing a more comprehensive survey with the JADES release using exclusively our own measurements. In addition, to determine absolute luminosity, which is critical, we assume that distance is proportional to redshift for all z. So what we see at a redshift of 5 to 6 is the blue dots are the near redshift, low redshift Galax galaxies. Those are disk galaxies, plotted surface brightness versus absolute magnitude in the NUV. The red dots are from JWST, and the green ones, the green triangles, are from HST. And you can see from the plots, and we did this statistically, there is no change in surface brightness, exactly as predicted from non-expansion. If we go out to a Z of 6 to 7, no change in surface brightness. 7 to 8, no change in surface brightness. And even up to 8 to 10, where there are no HST galaxies, we see absolutely no change in surface brightness.
Eric, could you just Could you just explain? I see a trend. Why they've, but you're saying surface brightness is constant. Why?
No, this is a trend
Yeah.
with absolute magnitude. So it's plotted surface brightness versus absolute magnitude. And we're comparing the blue dots are very low redshift galaxies, and the red dots are high redshift galaxies. So what we're seeing is that the correlation between absolute magnitude and surface brightness doesn't change in the least.
They're on the same track, right, Pavel?
Yes.
I mean, the surface brightness is correlated with the absolute magnitude, but not with redshift.
Yeah.
Yes. All right. So if we plot all of the data together, comparing the surface brightness at the same absolute luminosity, Galax versus these high redshift, for HST disks, which is blue, for HST ellipticals, which is red, and for JWST disks, there is absolutely no change over a redshift factor of approximately 400. The HST analysis have been published in these references. Of course, this is a complete contradiction of the expansion predictions. If expansion exists, we have to apply the z+1 cubed correction, and we get enormously brighter surface brightnesses for the distant galaxies than for the near ones. Now, of course, this could be explained by a change in the nature of the galaxies exactly compensating for the non-observed surface brightness dimming. But there are independent tests of the size of the galaxies. Spectra with ALMA show directly the mass, the gas mass m, and the rotational velocity v based on the width of the lines, independent of any assumptions about expansion. From Newton's law of gravity, we can get a minimum radius that is necessary for the dynamical mass to be greater than the gas mass, which of course is physically necessary. But in galaxy after galaxy, we see that if we derive the radius from the expanding universe hypothesis, there's as much as a gap of factor of 10 below the minimum radius. In other words, these galaxies would have dynamical masses as calculated if the universe is expanding 10 times less than their gas mass. Completely impossible. But with non-expanding radius, then this contradiction doesn't exist.
One minute.
Now, this could be considered an anomaly if it was not for the fact that all of the predictions of the Big Bang have increasingly been proven wrong by observation since 2016. We have large-scale structures which are 2 to 12 times too large and therefore too old. Lithium abundance is 20 times below Big Bang predictions. Helium abundance, twice too low. There's no evidence of baryon non-conservation. People have discussed the CMB is not Gaussian. It badly fits large-scale predictions. It gives a wrong prediction of the Hubble constant, a wrong prediction of density. And there is no evidence, as Pavel points out, for non-baryonic matter. The predictions of non-expansion have been validated. The interactions of magnetic fields, electric currents, vortex filaments, gravitation, and fusion reactions have correctly predicted the evolution of the universe. This is not steady state. We see the same phenomena occurring at all scales, from the laboratory to gigaparsecs. So why is this Big Bang hypothesis still so popular? It is the ENC, or Emperor's New Clothes effect. As we all know, it is difficult or impossible to publish papers that say the Big Bang is invalidated. You are stupid or unfit for your job. Because at the moment, The Ptolemaic method is used for conventional cosmology, not the scientific method. Hypotheses are derived from unquestionable assumptions. After wrong predictions, the theory is modified to fit previous observations. In the scientific method, hypotheses are derived from observations and are accepted only based on their correct predictions of future observations, which is ultimately the basis of new technology. So to summarize, the expansion theory predictions are contradicted. There is no expansion and no dense period of cosmic evolution. The redshift distance relation is not caused by expansion, but by something else that occurs to the light as it travels. Without expansion, the evolution of the cosmos can be correctly predicted using known processes of gravity, electromagnetism, and nuclear fusion. If cosmology is to be a science going forward, the Big Bang hypothesis must be abandoned. Thank you very much.
Thank you, Eric. Some one or two quick questions, please.
Indranil?
Yes. So I just wanted to ask regarding the source of redshifts, which is obviously an interesting problem in a non-expanding universe. So one thing I want to mention is that if we look at supernovae, for example, at redshift 1, then one thing we see is, of course, like by definition, the spectral lines are redshifted. But in addition, the supernovae take longer to rise and fall for the light curves. So if the photons were simply losing energy as they travel in some way, so for instance, in the tired light approach, then what would happen is the supernovae would still take the same amount of time for the light curve to rise and fall, but the photons would individually have less energy, they'd be redshifted. So I was wondering what you think of that.
The problem was referred to earlier is the circularity in the analysis of the supernova data. The supernova clearly expand more slowly. They are stretched depending on the wavelength that they're observed at. In other words, things happen slower at longer wavelengths just by the nature of the physical process. If you get the correlation between duration and wavelength, assuming the expansion of the universe, and then you plug that into the observations to try and derive the redshift duration, then you will get what you have put into the equations. It's a circular logic. If instead you simply calculate the 3 variable correlation to minimize the variability, then you get that there is no correlation between duration and redshift.
So if I understand correctly, what you're saying is the duration of a supernova has to be done like the so-called stretch parameter in the trip formula. That refers to a particular rest frame wavelength. And the conversion between like observed wavelengths and rest frame wavelengths, that has to be done more carefully. I think I understand what you're saying. We're facing similar kinds of issues ourselves regarding the circularity of how supernova analyses are done and whether cosmological analyses are baked in the derivation of the trip parameters. And if those trip parameters are then used to do cosmology, one can only hope to infer the same assumptions that one made.
Right.
Okay, thanks.
Thank you, Eric. Thank you, all the speakers of we are already running short of time. We have 40 minutes for a break, and we shall get back at 40 minutes later. Okay. Thank you. Thank you all.
Recording stopped.
Okay.
local and small to medium scale in astrophysics.
Hi, Sudha.
Hi, Mansi, how are you?
Yeah, right.
Yeah, great.
A quick lunch.
Okay, let me try to share this then.
Yeah. So we will be starting in 3 minutes, right? 3
Yeah.
or maybe 4 minutes. Yeah.
Sure.
Can you see my screen now?
Yeah.
Yes. So you can remove I can see the box.
Sorry. You mean?
Yeah, the
like
video
this?
box.
Just a sec. Okay, that should be fine. Might just leave it there in the corner somewhere.
So maybe you can just there is
Yeah.
a option.
That
If
should
you
be
will
good.
go to meeting, yeah. If you go to meeting control, then you can hide the video panel.
Okay, so if I go to
So there is more.
Meeting settings?
There is meeting settings maybe, yes.
And then
okay, so where is not the meeting settings.
No,
But
in general, if instead of sharing the whole screen, you can just share sort of the application, right?
let me try to stop the share and
share the specific window.
no, this doesn't really allow this. There's no option to share specific windows on here. But it's fine. I'll just
okay.
I'll
Yeah,
just
no
try and
problem.
minimize
That's all.
this. It should be fine.
Yeah, it's no problem.
Yeah. Yeah, that should be good enough, basically. Just leave it down there.
Yeah.
So how's everyone doing then?
Good. Should we start, or we can wait for 1 or 2 minutes?
Yeah, maybe wait 1 or 2 minutes.
Yeah.
You get the YouTube thing working as well, Elena, then?
Yes,
Yeah, it's
supposedly
working.
working. Yeah.
Okay. Is Alexia doing that, or are you doing that?
No, I'm doing that.
Oh, okay. Thanks. Okay, just another minute and then we can start, I suppose.
Recording in progress.
You can make it high a little bit. You can put it in the corner, maybe then.
Yeah, it's fine.
fill
I'll
the
just be
box.
careful to ensure there's not
Alright,
coming up anything
yeah.
important.
Okay.
Just tell me when I can begin.
Yeah.
Okay, thanks.
All right. Yeah. Welcome everyone. Welcome to session 2. And in this session, we are going to talk about local and small to medium scales in astrophysics. And our first speaker is Dr. Indranil Banik from Institute of Cosmology and Gravitation, Portsmouth. And his title of the talk is "The Observed Local Supervoid Could Solve the Hubble and Bulk Flow Tensions." Indranil.
Thank you. So hello, everyone. Welcome back to the meeting. So today I'll be talking about the Hubble tension primarily, which is one of the most important tensions in cosmology. So I'll explain how a local void might fit into that. So just want to highlight like a couple of papers which you see at the top left and my YouTube channel and some of the funding bodies that have helped with my work over the years. So what exactly is the Hubble tension? This arises because we have two different ways to get the present expansion rate of the universe. So the universe's size, if you like, is governed by a scale factor A, which is a function only of the time. It doesn't depend on position. And the expansion rate is parameterized as a dot or dA by dt. And by convention, in the scale factor A is chosen to be 1 today. It was smaller in the past, but exactly how quickly A has been rising with time is an important question, perhaps the most basic question in cosmology. Okay, so how can we get H naught or the A ratio A dot over A? which today is just the same as A dot. One way is to look at the very early universe, the cosmic microwave background radiation emitted when the universe was very young, was 1100 times smaller than today. If you were to look very carefully at the cosmic background radiation, you would see subtle variations in the temperature. And if you were to find out the typical variance in the temperature on different scales, you would be able to generate a power spectrum or a power spectrum, which is sort of shown in the graph on top of the CMB. To fit the pattern of peaks and troughs in this CMB power spectrum, you need a certain value for H0 in the lambda cold dark matter standard cosmological model, which, if fitted in this way to the CMB, does get some other things right, such as the primordial deuterium and helium abundances, and the galaxy cluster mass function at very low redshift. But it requires a certain value for H0 to do that, okay? So that's one way to get H0. It's very model dependent. Obviously, no one can see the expansion rate of the universe today by looking in the infant universe, but it gives you very precise value. Now, that's one way. The other way to get the present expansion rate of the universe is using the local universe and trying to figure out the expansion rate using nearby objects. So the way that works is you find the distance to an object, you find its redshift, Z, which is defined as the ratio of the observed wavelength to the wavelength of the light when it was emitted. You can use spectral lines for this. You subtract 1 from this ratio, that tells you the redshift Z. So it's a fractional increase in the wavelength. If you assume that this redshift is entirely from cosmic expansion, in other words, the difference in A over the time interval R by C for which the photon's been traveling, then you can infer H0. Now, the graph here highlights the Hubble tension. So the first part of the graph above the dotted line shows you the values of H0 that you get looking at the CMB in different ways, not just using the Planck mission, but in several other ways. And the lower part with all the other techniques shows you what happens if you try to use the local redshift gradient. So the local value of C, which is the speed of light, times dz by dr, or cz prime, in order to get the H0. So you could see there's a famous route using Cepheid variables and type 1a supernovae. There's a so-called distance ladder. But there's various other ways you can do it, and they all give fairly consistent results in this red vertical band, which is incompatible with the green vertical band coming from the early universe. So that, in a nutshell, is the Hubble tension. Now, one important way to find out which of these two values of H0 is actually correct is to look at the age of the universe, which, if you don't change anything else, will simply be inversely proportional to H0. So as you can imagine, if the universe is expanding faster, it must have had size 0 more recently. So the age of the universe times H0 is typically about the same in different cosmological models. Now, we can use the ages of objects for this purpose. So if you use 11 carefully chosen old objects, so mainly there's some individual stars, some globular clusters, ultrafaint dwarfs. If you use these and you take the inverse variance weighted mean, you get 14.05 plus or minus 0.25 gigayear. You also have to allow another 200 megayear, typically, is the assumption for these objects to actually form, because obviously the universe didn't start with stars in it already. But this figure of 0.2 gigayear has a factor of 2 uncertainty, roughly. Now, to convert this age into a value for H0, you also need to get a value for omega m, the matter density, which can be obtained without looking at the CMB, by looking instead at things like baryon acoustic oscillations and supernovae, without any calibration of either of these things. And that tells you value for omega m. So I'll come on to that in a sec. But basically, you can see these black points with their uncertainties give you the value of H0 from the observed age of the universe without looking at the CMB. That is much more consistent with the Planck value than the local redshift gradient, which is shown in this sort of purple band at the top. So it looks like at the background level, the Planck H0 is correct. Which means that the local redshift gradient must have somehow been inflated above what you expect from the expansion of the universe. Now, I've shown it in a different way here using this recent archive preprint. What's shown on here, the y-axis shows the Hubble constant in units of 100 kilometers a second a megaparsec. So that's the Hubble parameter today. The x-axis shows the fraction of the total of the critical density of the universe in the matter component. We're assuming the rest is in the dark energy. The CMB constraint is shown in this very thin gray band or ellipse with the white dot in the middle showing the most likely value. And the shoes value is shown in the yellow band. But the important thing is there are 3 additional constraints on here, which don't assume the local calibration of the shoes data set of supernovae, and which also don't involve like any kind of modeling of the CMB and isotropies and how they formed. So what are these? The red band is the vertical red band is the is from the shape of the expansion history as traced by supernovae and baryon acoustic oscillations, but without any absolute calibration of either of these things. The green band is from the peak in the matter power spectrum. So there's a turnover scale in it, which is basically because, for most of the universe expansion history, the expansion was like a power law. It was matter dominated. But at very early times, the expansion history was radiation dominated. And basically perturbations couldn't grow in that era because the matter was subdominant. So anyway, there's a turnover scale in the matter power spectrum, which tells you the epoch of matter radiation equality and what the cosmic horizon then. That's the green band. The blue band is what I was talking about from the ages of old stars. Now, importantly, you should be able to see that the red, green, and blue bands don't overlap, but these are only 1 sigma uncertainties. There is a narrow triangle in which they're consistent, but at slightly over 1 sigma tension with each of these, which is fine, right? And remarkably, the Planck CMB fit in lambda CDM is exactly in that region, whereas the shoes band, the yellow band, is higher. What this implies is basically the Planck parameters are almost certainly correct cosmological parameters, and the local shoes value is too high. But many different teams got that high redshift gradient locally. So how did that happen? That's obviously not due to measurement errors, by the way. So what is it caused by? The most likely scenario, in my opinion, is that it's caused by local structure. So we already know that redshifts don't just come from cosmic expansion, they also come from peculiar velocities, which are velocities in the rest frame of the cosmic background radiation. So for instance, the Andromeda Galaxy is approaching us. This is not because the universe is contracting, but because of random motions on top of the universal expansion. The impact of these peculiar velocities should become smaller as you look at larger and larger distances. But if, as the figure here shows, we are near the center of a large void, outward peculiar velocity, the outward peculiar velocity could start small, could rise, and then drop down only very far out. That could skew the local H0, because it depends on how the it depends on the gradient of the peculiar velocity field on its divergence. So that's how local structure could help. But is there a local void of the kind needed to solve the Hubble tension? And the answer is yes, there is very strong evidence across the whole electromagnetic spectrum for such a void, which we detailed in Hasselbalch et al. 2020. One way to see that is in the near infrared. So the graph on the left shows the galaxy luminosity function. And you can see it just shows you like the proportion of it that's been covered by the observations. And basically, Kyu-Hyun et al. Were able to see the majority of the galaxy luminosity function. Now, the important thing is the graph on the right, which shows you the co-moving luminosity density. Don't worry about the exact units on the y-axis, but it shows you the co-moving luminosity density as a function of distance from us. And you can see that the observations show a rise and then a flat level. This flat level is presumably the cosmological average density. But the dip towards low radii, that indicates we're in a void. And the point which we've circled is an average over the region indicated by the double-headed red arrow. So you can see that the density out to 300 megaparsec is perhaps half the average. So the as I say, the units on the y-axis are arbitrary, but you can choose it so that the flat level is 1, which is what the scale on the right side corresponds to. Okay, so there is strong evidence for a void, but is that likely in lambda CDM that we see such a void? So we looked at the Millennium XXL simulation, which is a large cosmological lambda CDM simulation. It's purely dark matter, so we got the total mass in halos using a semi-analytic approach. And we worked out the stellar mass in different regions of size 300 megaparsec, divided that by the mean for the whole box, accounted for the different volumes, obviously. Another important thing is that the density contrasts have been enhanced 1.5 times to allow for so-called redshift space distortions. So observers basically think they're looking out to some distance based on the redshift. They're not using redshift independent distances. Okay, this survey was using redshifts and getting distances. They were spectroscopic redshifts, but nonetheless you have to guess the distance based on that. However, if there was really a local void, that would lead to a larger local redshift gradient, which means that the actual distance to some fixed redshift would be smaller, and that in turn would mean you'd have fewer galaxies within that volume. But anyway, accounting for that, you get the blue bar, blue distribution, which shows you that density contrasts obviously do arise in lambda CDM, but the observations, which are shown in red, that includes also the observational uncertainty, by the way. The observations are obviously incompatible with the lambda CDM simulation. The tension is slightly over 6 sigma. So you can't get analogs to the observed KVC void in lambda CDM. But what is really interesting is that if you were to plot the underdensity on the y-axis and the ratio of the local redshift gradient to the actual value of H naught, then the observations, which are showing the red dot, are above and to the right of the green point, which is where you'd expect to be on average. On average, you'd expect no density contrast and the local and global values of H naught agree. But if there was an underdensity, you would move towards the top right, as indicated by the track with all the blue dots. However, you'd only be able to go up to the point marked 5 sigma using cosmic variance in lambda CDM. So that's how far you could get based on the typical density fluctuations we expect in lambda CDM. That is not enough to get you within even 5 sigma of the observed point. However, if you were to have more cosmic variance in lambda CDM, then you could imagine going further and further along the blue track. And at the point which is marked 10 sigma, you would get pretty close to matching the observations. Perhaps at 2 sigma conference, you could do that. Now, of course, in alternative scenarios where there's more cosmic variance, the blue track might have a slightly different slope. But anyway, this shows you that you might be able to match the observations. Also, by the way, it's very unlikely that there'd be some kind of error with the observations such that the local expansion rate is higher than the global one and we're living in an underdensity. these things would have to be unrelated observational errors. Seems very unlikely. So that's the basic idea, that there was more structure for growth than expected in lambda CDM. So to try and model that, we started with a small initial underdensity. We put in, so these equations are all completely standard, by the way. You put in Gn as the gravity, which comes from the extra mass enclosed within some radius, or actually the mass deficit. So if you imagine working out the mass that should be there within some volume at the cosmic average density, looking at the actual mass there, finding the mass deficit, that's what drives the an extra acceleration term. So that's all standard. We've seen that won't be enough. So we enhance the gravity according to the Mond prescription, which I'm not going to go into any more detail, but suffice to say that it enhances the strength of gravity. So that gets the structure growth to follow these blue tracks, which show the growth of density fluctuations on a 300 co-moving megaparsec scale in Mond, whereas in the Newtonian case, they follow the red tracks, which are much shallower. So you can see that structure formation is indeed enhanced a lot in Mond, which was the idea here. But how does that help us? Before I get on to that, I want to explain that redshifts, we have to be careful, are not purely due to expansion of the universe. You have this equation up here for the ratio of observed and emitted wavelengths, which has the usual term for the expansion of the universe, the 1 over A. But there's also a Doppler term for motion along the line of sight, and gravitational redshift term, which I've abbreviated as GR. So that is because if we were living in a void, we would be sitting on top of a potential hill, and photons would have to work their way up it, and they would lose some energy doing so, leading to additional redshift. So what I wanted to say is cosmological parameters are inferred from the redshift by equating the redshift with just the first term, just the 1 over A term. In other words, people assume that lambda obs over lambda emit is 1 over A, which is wrong in general. But if you assume that, you get a so-called A app that's apparent A, a cosmologist who doesn't really know what they're doing would infer. Then you've got the actual A, which in general is unknown, but we can work it out in our model. That leads to some value for delta A, which will in general depend also on how far back in time you're looking. So if you take the delta A differentiate with respect to time, that obviously is related to the amount by which you misestimate the Hubble constant. So by looking at all this, we were able to find what observers would infer for the Q0 bar parameter, which is a so-called acceleration parameter related to a double dot, or d2a by dt squared. And for the H0, of course, what should have happened in the Planck cosmology is we should be at the green point, but the observation is at the black point with their uncertainties shown with these error ellipses. The different void profiles managed to fit really well. So you can see the Maxwell-Boltzmann profile, the star is up here, and the square and the triangle for the Gaussian expansion profiles, they're at almost the same point. You can't really distinguish them very easily, but they're at the same point. So they all match pretty well. That means this model can solve the Hubble tension. But what about other tests? So first of all, in this model, we have a very simple model where there is spherically symmetric outflow from a void, plus we apply a Galilean transform to the void as a whole, so it's moving in some direction as a whole. Therefore, to get the CMB frame velocity, you'd have to add the two components together using the cosine rule to get the total. This is just an illustration, of course, but the idea is that the red cells correspond to the bit of the void in which the velocity is compatible with the observed peculiar velocity of the local group, which is the largest sort of reference frame to which we can transform ourselves without any controversy, because we know the motion of the sun within the Milky Way, and we know the Milky Way and Andromeda relative motions. one thing that people wonder is, do we need to at a special location in the void? And the answer is not really, no. Because if you see here, the color shows the velocity in the CMB frame, and the black contour shows all the points where the velocity is equal to the local group peculiar velocity. So if you want to ask the question of how unusual that is, you could ask what's the likelihood that the peculiar velocity is even smaller than 630 kilometers a second, which would correspond to the whole region within the black contour. And that's obviously a sizable part of the whole void. Therefore, our position in the void is not fine-tuned in this model. Now, let me see what's gone wrong here. And this is just showing that that the observations correspond to about 2.536% with the model. I can show the different constraints that we considered in the Q&A if anyone asks. There's a pie chart in the appendix showing all the different considered constraints. But suffice to say that we can match the observations fairly well. But turning back to the void velocity field, we did a more detailed test of it using the so-called bulk flows, which I'll come on to in a sec. But basically, the idea is that redshifts are partly due to cosmic expansion, partly due to the Doppler effect, that's obviously very hard to disentangle. But our location in the void obviously will be somewhat off-center. And as a result of that, the apparent expansion rate would depend on exactly which direction we look. So can we use that? Right. So we to try and test that, we use the so-called bulk flow. Just a sec. Let me. Yeah, that's better. We use the so-called bulk flow, which is essentially the average. Ideally, what we would get is the average of the 3D peculiar velocity vectors within a spherical region centered on our location. But we have to make do with only the line of sight peculiar velocity, which we can treat as a vector pointing on the line of sight. So when I say the line of sight peculiar velocity, think of that as a vector quantity, not as a scalar. We can take the average of these line of sight peculiar velocity vectors, weighting the galaxies in a certain way, which we won't get into, and just take the weighted mean of these peculiar velocity vectors. However, the final result then has to be tripled. So what that means is that if all galaxies within some region had the same 3D peculiar velocity, so the bold V, then what you would get from applying this observational procedure, you would infer a bulk velocity of V bulk, which is actually equal to V, despite the projection effects. That's because of the factor of 3 I just mentioned. So the other important thing, you might be wondering, well, how, okay, observers can get line of sight motions from redshifts, but how can observers get line of sight peculiar velocities? Because they don't know the value of the Hubble constant. The answer is that assumed H0 has no effect on V bulk. So whatever value of the H0 you assume, it doesn't matter because it will simply put a spherically symmetric, it'll affect the velocities in a spherically symmetric manner, which will not affect the average. So the bulk flows that were, we compared our model with the bulk flows observed by Tully et al. By Watkins et al. 2023, based on the cosmic flows 4 catalog by Tully et al. UX, UY, and UZ refer to different directions. So they're saying the bulk flow is a vector quantity. But the important panel is the bottom right one, which shows the magnitude of the bulk flow as a function of distance. You can see the points in green are way above the expectation of lambda CDM in red. And the blue line shows an estimate of systematic uncertainties, which of course grow a bit with distance. The important thing to understand is that because the results here are independent of the assumed value of H0, the bulk flow tension is independent of the Hubble tension. Okay, so how significant is this bulk flow tension? Well, you can see here the likelihood or the percentage probability of matching the observations in lambda CDM. the tension rises as you go further out. If you go beyond about 230 megaparsec over little h, then there's more than 5 sigma tension. But the important thing to understand is that on this scale of about 300 co-moving megaparsec, that's about twice the scale of the first acoustic peak in the CMB. There's no evidence for any kind of anomaly there. So this tension indicates that structure has grown faster since the CMB was emitted than expected in lambda CDM. It's not a sign that we need to change the initial conditions as such. Now I'll get on to some important results. We considered varying how far we are from the void center and also the velocity of the void as a whole. We put ourselves only along the symmetry axis of the void. So basically along the axis of its systemic velocity. This heat map shows the chi-squared compared to the observations. Now we have 9 data points from the bulk flow curve and 2 degrees of freedom, as you can see. So ideally we'd get chi-squared below 7. Interestingly, we can actually do that for some models. Now, in case you're wondering why there's like 2 sort of valleys in the chi-squared, that corresponds to the inner and outer solution. So basically, you can see here that if you were on the x-axis, you could be either at slightly below 200 megaparsec or at around 500 megaparsec. And at both places, you'd be sitting on this black contour, which is a locus of points where the peculiar velocity matches the local group value. So because of that, there's always these inner and outer solutions. But we can match the bulk flow curve pretty well. Now, that's with the exponential one. With the Gaussian one, again, the conclusions are similar. In both cases, the outer solution is disfavored. Only the inner one seems to really work. Because we're fairly close to the void center, the CMB, the low L multiples of the CMB would not be much affected. So we've already discussed the CMB dipole, of course, but the CMB quadrupole is not much affected, and higher order multiples, again, not much affected by lensing due to this proposed void. So that's with the Gaussian. With the Maxwell-Boltzmann, this, by the way, the void isn't deepest at its center. The density gets back up to the cosmic mean at the center of the void. This can be made to fit pretty well in some scenarios. It needs much larger offset from the void center. And interesting, the offset's similar for the inner and outer solutions. But it can still kind of work. So what do our best fitting results look like? Well, you've probably seen already from the low chi-squareds that it is possible to get a very good fit. So what's shown on here, the solid curves show the inner vantage point, the dashed curves show the outer vantage point. The different colors show the different profiles. You can see, though, in the table that in the exponential case, we can get to an overall tension of only 0.3 sigma. So that's like for 7 degrees of freedom, if you work out the likelihood of a higher chi-squared for 7 degrees of freedom, that corresponds to 0.3 sigma tension for a single Gaussian. That's obviously totally fine. And you can see here, these curves nicely go through the data points. So we can match the bulk flow curve. What about other tests? Well, one thing that should happen in the local void scenario is that the Hubble constant, H0, that you infer from data at higher redshift gradually gets back to the Planck value. Now, obviously, if you were looking at higher redshift, you have to make some assumptions in order to get H0 out of it. Actually, that's true at any redshift. But basically, the Hubble tension should disappear if you look beyond the void. That's why our models have these curves that go down from about 75 to about 67, right? Now, the bands on here, the blue band shows the Schu's value, the dark green line with the little error bar at the left, that shows the Planck value, and these pink bands show the age constraint. So you can see that our models more or less match the observations from Gia et al. 2023, and also a more recent update to their work, Gia et al. 2024. So we could more or less match this declining trend of the inferred H0. Now, when we try to look at supernovae, what we found is that if you model it, that the Hubble parameter is equal to the Planck Hubble parameter. So remember, this depends on redshift. But then if you add some extra term, which is sort of representative of the local void, then what happens is showing the contour plot. Before I get onto that, I'll just explain that we've included a chi-square penalty based on the age of the universe. But that doesn't include the delta H0 adjustment, because we're assuming that that's happened due to outflows induced by a void. It's not representative of the actual expansion rate. So here, what you can see, the inference on the delta H0 is inconsistent with 0. It clearly allows values around 7-8 kilometers a second a megaparsec, which is needed to solve the Hubble tension. But in terms of the omega m and delta H0, I mean, the red point is essentially where a local void solution would need to lie, approximately speaking, in order to be a reasonable local solution. And you can see that it's more or less consistent with the observations. At least, I mean, we're not going up to 3 sigma. The PyGTC doesn't allow that, but it allows us to go up to 99% confidence. And we're more or less able to match all these constraints. So remember, this is only using supernovae. We haven't included other constraints here besides the age. Okay, so that's with the supernovae. Now, in the last 10 minutes, I'm going to explain the Baryon acoustic oscillations, which are a crucial test of cosmological models. Now, how exactly do these arise? So the idea is that the sound horizon at recombination was frozen in place. So remember, you have this peak in the CMB. Well, the oscillations sort of stop once recombination occurs and electrons and protons combine into hydrogen atoms, because these are now neutral and they're not really affected by radiation anymore. So the angular feature you see, this sharp peak, basically is also imprinted in the large-scale matter distribution. So the co-moving length scale of the first acoustic peak, the time of recombination, should be visible in the large-scale distribution of galaxies at later times. Now, that's what the panel on the right is showing. It's showing the sort of correlation function of galaxies, how clustered they are on different scales. And you can see that, of course, there's less clustering on larger scales, but there is this huge bump in the middle. That's the BAO bump, which, and all we're using, importantly, is the length scale of that bump. So not the height of it, which depends on various other factors that we're not really interested in, but on the length scale, or in particular, the angular scale it corresponds to. So if you were to do this in 2D and plot the correlation function as a in terms of both the separation along the line of sight, which is the y-axis, and in the plane of the sky, which is the x-axis, and sort of divide out the smooth pattern in the correlation function, you'll get this nice ring feature, and that's the BAO ring, which is, you can either try to fit like a circle to it and get the radius of the circle, or you can measure the across and up. So you can measure the width and height of this feature. So what are the actual BAO observables? The actual observables are the angle of the BAO feature, which is the co-moving length of the ruler divided by the co-moving distance to that to the epoch at which you're observing. That corresponds, of course, to orienting the BAO ruler orthogonally to the line of sight. There's also one for the parallel to the line of sight. The way you do that is you find the redshift depth across the ruler. So if you imagine orienting the ruler parallel to the line of sight, then light from the far end of the ruler must have been emitted earlier to reach us now. The universe has expanded more in that time, which means it will have a higher redshift. That's all true in a homogeneous cosmology, but also similar idea in a void. In a void, what will happen at a fixed distance to us, the redshift will be higher. or equivalently at the same redshift, the distance will be smaller. So a void will have the effect, of course, of inflating the redshift for any fixed look-back time. For the parallel BAO observable, the void also affects the extent to which the far end of the BAO ruler is redshift compared to the near end, because you have to account for the evolution of the void itself and also like the velocity field of the void. So that's all fairly straightforward. Well, it's standard anyway. The bit about the homogeneous cosmology. Now this is essentially what the BAO looks like. The triangle at the top right kind of illustrates it. Now, if we try to look at the ratio of the co-moving distance to the co-moving distance in lambda CDM. So really what this is plotting is the angular scale of the BAO feature divided by the angular scale that you expect in lambda CDM at the same redshift. Okay, and that's important. It says we have the same redshift. So obviously in lambda CDM, what should have happened, all the points should have lined up along a flat horizontal line at 1. There's a slight amount of uncertainty in it because the size of the co-moving, the co-moving length of the ruler has a small uncertainty, but you can see the points are generally all below that line. And in our models, well, the best models we think are the solid red and blue models. The dash models show what happens if you ignore one of the terms for the gravitational redshift, if you ignore that, but that should be included. So only the solid lines should be considered. And we think if you look at the solid red and blue lines, it seems to fit the data better than the flat line at 1, which is expected in lambda CDM. All these different measurements sort of color-coded. We've also used a larger marker size for the more recent measurements. That's just to make it a bit easier to see what is going on. So you can see here, that's with the angular scale of the BAO ruler. What about with the redshift depth? Well, here it's less clear because we've lost some of the data at low redshift, which was important. So it's not very clear whether the void model would be preferred here. But also the expected signal is much smaller because the void outflow velocity decreases at large distances. That partially cancels the overall effect of the void of inflating the redshift at fixed distance. That means when we come to do the Alcock-Pezinski test, which involves basically taking the ratio of the previous two graphs, that removes sensitivity to the size of the BAO ruler, which, as you saw, was very small anyway. But it also raised the uncertainties quite a bit. And that means that the Alcock-Pezinski test, as it's called, doesn't really tell us too much just yet. However, there is another way of looking at things, which is the so-called isotropic average. So if I just quickly show you that on this graph, if you were to fit a circle to the BAO ring, not measure like across and vertically, but fit a circle to it, then in case that whole feature is pretty faint, you would get more reliable results. So getting this isotropic average is easier for an observer. That's why there's more points, and the points on here have smaller error bars. So this is supposed to be particularly discriminative. In our void model, we can also predict like what this feature what this quantity should have been. And if you do that, you can see that these solid red and blue lines actually fit the observations better than a flat line at 1. I mean, obviously, there's a few points which are discrepant with the void model at like 2 or 3 sigma, but that's to be expected given how many data points there are. But in general, the points all lie below the solid line at the horizontal line at 1, below the gray band. And you can see also the recent DESI measurements with these solid large red points. And they're large because they're collected more recently. But they're not the only points. We're showing like essentially all the measurements we could get our hands on over the last 20 years. So what do we conclude from this? Basically, one important thing to understand the local void scenario was not proposed to solve the Hubble tension. Galaxy number counts show that we are in a significant underdensity, irrespective of what you assume is the value of the Hubble constant. There's good evidence across the whole electromagnetic spectrum from radio to X-rays for that. I've mostly focused on the near-infrared in this talk, but you can see it in other ways, like in radio and optical and so on. So papers about this in SDSS. Now, given the nearly uniform initial conditions that we can see in the cosmic background radiation, this requires significant amounts of outflow to have reduced the local density to the extent that it obviously has been reduced below the cosmological average. That in turn would cause the locally measured redshift gradient to be larger than predicted by about 10%. Now, this is assuming that the ΛCDM model has actually got the correct prediction for the expansion rate today at the background level. If that's the case, then this void would induce a difference of about 10%. That's just a quick back of the envelope calculation we did in Hausegger et al. 2020. Using the observed depth of the local void. Because of that, we were able to link the Hubble and void and KBC void tensions for ΛCDM in a semi-analytic model, which is the Hausegger et al. 2020. The model can be used to predict a bulk flow curve. So that depends also on where exactly we are within the void, which wasn't really constrained in the Hausegger et al. 2020. But nonetheless, it is possible to get a very good fit to the bulk flow curve using the model parameters that we published in Hausegger et al. 2020. We haven't changed the model parameters. We've just had to adjust where exactly we are within the context of those void models with the same parameters. The ages of old objects in the galactic halo return the Planck H0, indicating that the value of A dot at the background level is actually the Planck value. Okay, that in turn means that the local redshift gradient has been enhanced by non-cosmological contributions to the redshift. Now, we have heard some arguments on whether that can be due to tired light, but my opinion is the most standard interpretation is that it's just due to peculiar velocities, which are the not controversial, that peculiar velocities can create non-cosmological contributions to the redshift. If we try to infer H0 from data at high redshift, you get the Planck value again. So the Hubble tension doesn't persist like at high redshift. It's a local effect. So one thing I didn't mention was that cosmic chronometers can also be used to get the H0. And there was a paper from very early this year which also got the Planck value. What was saying? So early time solutions have also been argued to face very severe difficulties, which I won't go into right now. Just to finish up, I want to mention that very few solutions have been proposed to the Hubble tension, which weren't actually proposed in order to solve the Hubble tension, but were proposed for some other reason, and successfully predict something else that was later observed. So obviously, in our case, a critical aspect of it is that peculiar velocities are much larger than expected in ΛCDM. That's the only way this can work. That anticipated the bulk flow observations of Watkins et al., which show just that, and not only that, but the actual details of the bulk flow curve that Watkins got, we are able to match. So that's it from me. Any questions?
Thank you, Niraj. So any questions from the audience? Okay, Louis Marlant. Okay, Louis, you can go ahead.
I'm just trying to make this clear in my head. You're saying that the under density is well, you're showing it's apparent in many different measurements, So, but then this implies that there's a problem with lambda CDM.
Yes.
And then, but then if there's a problem with lambda CDM, wouldn't that have an effect on the value of the Hubble constant, like the 67?
Not necessarily.
Like it seems if you're going to this through different ways, one of them shows that the other one is not right.
Not necessarily. I mean, it depends on where the modification is. What we think is going on is that gravity is modified at very large distance scales, certainly beyond a megaparsec. And because of this, the expansion of history of the universe and the oscillations, the sound waves propagating in the early universe wouldn't really be affected. So that's why, and we think that this is reasonable. We've also argued that the lensing sort of distortions due to a local void on the CMB which affected at low L would also not really be very important. So we think that if you did have a large scale sort of modification to gravity, it might not really affect the Planck value for H0. Yeah.
Really? Okay. Like modifying gravity in the early universe would not change.
But it's not in the early universe. It's on large scales, right? On scales beyond what this modification on large scales would not matter in the early universe, because modes on scales of perhaps 10, 20, 30 megaparsec would only enter the horizon when it's maybe 100 million years old. So modifications of gravity on those scales wouldn't affect the early universe. It's more like a late one. This is really a late universe modification.
Okay. I see. Thank you.
Yes, another question. Pavel.
Hello. Yeah, thanks, Indranil, for this very nice.
You can go ahead.
Yeah, thanks. Very nice for this. Thank you for this very nice overview, Indranil. And there are two sort of questions. The first is a comment to the question just now. So Nick Samaras will give a talk tomorrow, and it is entirely possible that the global Hubble Lemaitre constant will change, because one has to now refit to the CMB in terms of the new cosmological model. But otherwise, you're right, Indranil, that it doesn't have to affect the global expansion, this local void, but it does change the cosmological model. And the other question, we have discussed this before, but why do you think this clear solution to the Hubble tension is not generally much more discussed, right? Because it seems to be completely clear that it's like extremely relevant, probably, well, very realistic. It's in the sky, so to be speaking, from whatever point of view one looks at it, right? So,
that's actually a very good question. I was actually just at a discussion about the Hubble tension at Portsmouth and at a Cosmology Institute. And to be fair, some cosmologists are starting to discuss it more. One issue, I believe the main drawback that I've heard so far, well, there's two drawbacks, but one of which isn't a real one. One of these is that people haven't yet seen the Baryon acoustic oscillation results, so they don't really understand that a local void model could provide a good fit to the BAO results, which I've shown actually can be done. But the other thing, but we haven't written that up yet. The other thing is that the supernovae seem to show that there is apparently, they don't show a return to the Planck cosmology when you go further out. But this hasn't really been demonstrated properly. But apparently a lot of people think that doesn't happen for reasons that are not really very well thought through. It's because, however, it's not been demonstrated that the supernovae do definitely get back to a Planck cosmology at high redshift either. I would say that's not yet clear. So, but the supernovae and the BAO are the main objections. as in, because the BAOs seem to show that there's no deviation from a Planck cosmology at low redshift. That's what people believe. That's obviously demonstrably wrong, as you can see here. So once we write this up, that should be clear. But with the supernovae, one has to do a detailed analysis accounting for how exactly you apply the so-called trip parameters. This is something like Eric Lunn was talking about as well. Like you have to, unlike BAOs, where you're just looking at a geometric feature like an angle, with supernovae, you're looking at a luminosity, but luminosities have to be corrected because not all supernovae are the same. So you have to apply these stretch and color corrections. And that requires you to have knowledge of the so-called trip coefficients. And how exactly do you get them? You assume a cosmological model to get them. So if we were to assume if we were to allow a return to the Planck cosmology at high redshift while fitting for the trip parameters, then we might see something interesting, but this has not been done. That's one of the things I want to do. But it's because of these things not really having been done yet, or at least not being published yet in this case. That's why people are a bit hesitant to embrace the local solution. What is interesting, though, the main alternative is an early time solution. And regarding early time solutions, I was actually asking if anyone in Sportsworld wanted to advocate that after having explained my idea. And what happened interestingly was, instead of people advocating it, there were many people who explained why that doesn't work without even mentioning the age constraint, incidentally, which I think is one important reason why it doesn't work. So people are gradually starting to accept that late time solutions might be needed, and indeed discussing issues with the calibration of supernovae, while for the BAO results, people just have obviously not looked at it yet properly. Well, there are actually discussions about BAO results not exactly agreeing with the Planck cosmology, but no one's really interpreted that as possibly due to a local void. That's when we write this up, that's obviously what we're going to try and do. But that, I think, is the reason for it.
Okay, thanks.
Okay, Eric, go ahead.
Yeah, just commenting on the supernovae.
Yeah.
I mean, you can statistically analyze supernovae without assuming a cosmological model. In other words, there are standard statistical methods of multiple variable analysis.
Oh, that's the kind of thing we're trying to set up, but you can't do it without a cosmological model altogether, because there's too few supernovae at very low distances where you have redshift independent distances.
No, but the point is there are standard statistical tools
to do what?
That minimize the variance in a multiple variable situation.
That's what we're trying to set up, but this can't be done without a cosmological model altogether.
Yes, it can. Yes, it can. Mathematically, you can take these you can take wavelength, duration, redshift, luminosity, simply as raw data and plug them into standard statistical formula that minimize the variance in the relationship among the variables. So the overall variance
So you mean
minimized.
So I think what you're trying to say is that it's possible to sort of reconstruct some arbitrary relation between luminosity distance and redshift and minimize the residuals about this relation.
That's right.
Sure, that's exactly the kind of thing we're trying to set up, but I'm not sure that's been done yet.
Well, yeah, I did it with data that was provided by, whoops, I'm blanking on the colleague's name, but I didn't have access to the raw data that he used. So I think that you're correct in saying, I don't think this analysis has been done using the actual raw data that the measurements are based on. That would be very interesting to do.
But that's partly what I'm trying to do.
Yeah. But you can do that without any assumption.
Next. Because okay, next question we have G Ullas, if I'm pronouncing it correctly. G.
Sir, yes. Sir, how do the BA measurements of angular scales and redshift scales helps in refining the constraint on the cosmological parameters, like in particular in relation to the expansion rate of the universe, like that?
Sorry, your question is about how do BAOs help?
BAO measurements of the angular scale and redshift scales.
Right. So basically, the way it works, BAOs can tell you the ratio between the size, the co-moving length of the ruler, and the co-moving distance to a certain redshift, which depends on the cosmological model. In case you're wondering how, like in a scenario where you don't know the length of the ruler, but you just assume this co-moving length RD remains constant, what BAOs can do, they can tell you the shape of the expansion history. So they can tell you like the form of A of t, but they'll be invariant to a scaling. So A of t goes to A of 2t, for example, making the universe twice as old with half the Hubble constant. BAOs in that scenario will not be able to distinguish those two cosmologies. So without any calibration, BAOs can't tell you H0, but they can tell you omega m. That, roughly speaking, is how BAOs can help. But they could certainly contain important information, right? Because whatever the co-moving length of the ruler is, that's the same at different redshifts. But obviously the co-moving distance to that redshift changes, and therefore the angular scale of the BAO changes. And the way it does so obviously is important in cosmology. Does that answer your question?
Okay, sir. Thank you.
Sure.
Yeah, again, Luis, do you have any question, or was it before?
Just a short comment. There's a paper that is about calibrating supernovae with a different technique that doesn't involve the intensity of the light, but more the shape of the spectrum. And I put a link in the discussion. It might kind of help clarify, or help getting a better distance estimate from supernovae. It's already 3 years old, but I think it was a good paper.
Well, that doesn't necessarily match. I mean, the original TRIP paper that people still use is more than 25 years old, and
Sure.
Thanks. I'll have a look at that. I mean, the way
it's just a new method. It's a different method.
Right.
It's called twins embedding. Maybe you've heard about this. But
the twins what?
Twins embedding. They're comparing pairs of spectra.
I don't think I've heard of this. I mean, in the standard way, like you have to do the standardization, you have to know the so-called stretch and color parameters of a supernova.
Of course, yeah, that's the standard way by Adam Rees and Perlmutter. Yeah.
Yes.
I put a link in the discussion.
Sure, I'll have a look. If there's other ways to do it, that's certainly very valuable.
Yeah, I think it's a very convincing way also. So, yeah, have a look. Thanks.
I have a quick question. After fitting your model with the bow data, what is the value of H0 you expect? It should be lower or higher than the Planck value?
Our models assume the Planck cosmology at the background level.
Okay. So you expect the H0 value to be like 69 to 68.
Right. So it depends what you mean by that exactly. If you're asking about the value of A dot, then we expect it to be 67.5 because that's what we need. But if you're asking what should an observer who gets a local redshift gradient measure, the answer is basically given up here. So that's given by these blue points. So the local redshift gradient that an observer should measure, so C times dz by dr, that would be higher than 67.5. That would be about 76 or so if they did an analysis in which, if they were doing like a second order fit to the distance redshift relation. That's with both the linear and quadratic terms free, because in general that's needed to get the accurate results. So the local redshift gradient would be higher than in the Planck cosmology, but the value of A dot obviously would be the same as in the Planck cosmology, because that's what we've assumed is correct at the background level. But we're not extracting a value for A dot from the BAO data. This isn't an analysis like that. We're fixing the model parameters at the Hausegger et al. 2020 paper and seeing if we can fit the latest data using that. So we haven't actually fit the BAO results. Like there's no model fitting in any of these results. We're just taking the models as published almost 5 years ago and seeing if they work.
Okay. Great. All right, thank you. Any more questions we have? I'm not seeing any questions, so thank you, Indrajit, for your talk. So we can move to contributed talk for 15 minutes. And our next speaker is Jenny Wagner from Helsinki Institute of Physics, University of Helsinki. And the title of the talk is Abel 3827 and its constraints on dark matter and MOND.
Yeah, thanks
Jenny,
a lot for having
whenever
me.
you're ready. Yeah.
Thanks a lot for having me. And yeah, good morning, good afternoon, and good evening, wherever you are. So let me quickly share my slide. So, do you see the screen?
Yeah.
Okay, perfect. And do you see my mouse?
Yes.
Yeah.
Okay, great, wonderful. So, Alice in Wonderland said that she had often seen a cat without a grin, but never a grin without a cat. However, if we look at dark matter, then we pretty much look at a grin without a cat on cosmic scales. And therefore, I would like to tackle the question now, what do we actually know about dark matter, if it exists, and which of its properties are more or less driven by model-based assumptions that we use in addition to the data-based evidence that we have. And entailed, I would like to ask, usually people use examples to refute MOND. So if we replace dark matter by MOND or by other modified gravity theories, can we actually refute these theories based on single examples? Spoiler alert, the answer is no. But let me first introduce to you our working example for the next 15 minutes. This is the wonderful galaxy cluster 3827, and it's a unique test bed to answer all of these questions. We have 55 spectroscopically confirmed member galaxies, and they put the galaxy cluster at about redshift 0.1. This is one of the closest galaxy clusters that we have with all of these observations that we have collected. Zooming into the core, we find another peculiarity, namely we encounter 5 more or less equally bright galaxies. So this cluster is not relaxed, it hasn't a single brightest galaxy, but it has a highly dynamical structure here in the core. Another peculiarity that's also easy to spot is the strong gravitational lensing effect around these galaxies. So we have 5 highly detailed and magnified multiple images from the same background source, which is supposed to be at redshift 1.24. There might be an additional gravitational lensing system, which is follow-up studies, because it has a very low redshift of 0.41, and therefore it might be just an irregular galaxy, but based on the shape, it rather looks like it could be another strong lensing event. So, given all of these data, I would now like to ask, what can we infer about the mass distribution of Abel 3827 based on the strong lensing constraints that we have here? So what is strong gravitational lensing, for those who don't know? It's pretty easy. We assume that GR is our theory of gravity, And the only assumption we make in addition is that light is deflected by heavy mass distributions that curve the spatial structure underneath it. So emitting light rays from a source here, we do not see a single image like the source itself, but the light gets deflected into multiple pathways around this strong gravitational lens, this heavy mass density, such that we see these multiple images which are highly detailed and highly magnified. Some are even demagnified. But the point here is that if we have a highly symmetric lens, for instance, a spherical galaxy, then we also see highly symmetric multiple images. For instance, for this perfect alignment where the source is exactly behind the center of gravity here, we see a so-called Einstein ring around the spherical light-bending mass distribution. But if we go to higher scales, to galaxy group scale or even to galaxy cluster scale, these multiple images obey less and less symmetry. And so for galaxy clusters, which is just a bunch of galaxies and maybe a dark matter halo underneath, we just have these giant arcs here somewhere in this region where the galaxy cluster sits along our line of sight. So how does this strong gravitational lensing effect in Abel 3827 now comes about? Well, if we take a look at our galaxies in the core, we find that they are distributed in a region of about 10 megaparsecs of extent along our line of sight. And this is about 4% of the total distance to us, which is about 400 megaparsecs. So we have quite a lot of galaxies, and this extent is one order of magnitude larger compared to other galaxy clusters at higher redshifts, so these 4%, because the galaxies at higher redshift, they have a negligible extent compared to their overall distance to us. So how do we now model this strong lensing effect here? Well, we could be the most realistic as possible. We could assume that the light emitted by the source hits all of these individual galaxies as gravitational lenses individually. And then we would have to stack all of the lensing effects individually. This is the so-called thick gravitational lens approach, and it is a smoking gun to have a thick lens if we have relative rotations between the multiple images, and if we have a really close-by structure that is lensing. We also expect washed-out signals because we do not have an individual lens, but several lenses at approximately similar redshift. But this is, as I told you, galaxies at high redshifts do not have relevant thickness. This is not what we do in the standard formalism. What we do is we project all of the individual galaxies into a single thin lens, and we assume that this effective two-dimensional mass distribution is now our strong gravitational lens. As a consequence, we cannot produce relative rotations between the multiple images anymore, and we expect a rather clear lensing signal. So let's now use this thin lens approximation the easiest way possible and see how far we get for Abel 3827. And now my colleague Nicolas Tesori and I, we developed an approach in order that we do not have to reconstruct the global distribution in the entire lens plane, but we would like to stick to the information that is directly contained in the data. And we took, all of these galaxies come from the same source. So we took all the multiple images and we identified features in all of these images that we could match onto each other. So to leading order, it is possible, based on the observations, to set up a linear map that maps image number A here into image B. This is a totally observation-based transformation. But if we take the lensing formalism, we can use the so-called distortion matrix here, which encodes the local shearing properties of all of these all of the masses along the line of sight between image A and the source plane. So we can use this local distortion matrix to back project image A into the source plane, and we use the inverse distortion matrix for the line of sight to image B in order to do forward project into the lens plane again. So this linear transformation then encodes a product of these local distortion matrices. Without making any assumption where there is any dark matter in the global distribution of the mass density. And if we have at least 3 multiple images with 3 features in each image, we can uniquely solve for local lens properties that amount to the relative mass densities between the multiple images, mass density ratios, and at each image position, we can get something that is called the local reduced shear, which is the distortion, the shearing property of each multiple image weighted by the mass density that is there along the line of sight between the source and the image. So these are the local lens properties that we can get, and this is the maximum information that all lens model-based approaches that reconstruct the global mass density distribution have to agree upon. Now, what does this mean when we apply it for Abel 3827? Well, we first need to make sure that we don't have any transient contaminants in our data set, and we check this. And second is, we also need to make sure that we are identifying features in the background galaxy and not some foreground features, for instance, globular clusters along the line of sight or stuff in the galaxy cluster, which is the foreground lens. And if we compare now the color-based HST stacked images that previous works used to identify features and our blue HST filter band, from which we robustly extracted, based on an image processing algorithm, all of these features that we marked here, we found that there is a spot here which doesn't show up in our image processing based algorithm, but which seems to maybe contain foreground contaminations. So what's the impact of misclassifying a foreground contamination as a potential feature, and what does it make to the local lens properties or even to the global lens properties? The second question we have to ask is, what are the ambiguities in the matching process? What happens if we identify different features in one image with different features in the other image? What is the true feature matching? And here we again found ambiguities, because in our approach we found that it is possible that these 2 multiple images here close to galaxy G1 can have a relative orientation that is opposite to each other. They are of opposite parities. They are mirror images. And the previous works that analyzed the dataset, they assumed that these 2 images are of the same parity, which is not the standard configuration that we would expect in strong gravitational lensing. And this entails usually that we need more shearing from external masses in order to get these parities to be in the same direction, while it takes less shear to just get a standard fold configuration. So how do we now make sense out of all of these ambiguities? What's the impact on the reconstruction of the dark matter, of the total matter, and in the local lens properties? And our approach is the first one that can clearly track all of these changes, because we can dissect the reduced shear into an amplitude and into a direction, and we can run our algorithm on all of these different choices and then plot the different results for the reduced shear in direction and in amplitude. And here, for the 3 multiple images of this giant arc, you can clearly see that all of these different choices amount to different directions and to different amplitudes in the reduced shear. So now we have a clear understanding how the features that we choose are directly linked to the local shear properties of the strong gravitational lens. Another important point here is that if you take a look at the multiple images, they are quite large compared to other multiple images in other galaxy clusters. And we found that our algorithm cannot be applied to the images as a whole. What we needed to do was to chop it up into smaller regions and get the local distorting properties in each of these regions, and we found that they change across the regions. So we do not even have a constant mass density over the size of these images. This was also quite unusual, and so we concluded that if the properties already change over the multiple images, how can we infer any properties of the mass distribution at the position of these galaxies? We don't know. So this means that the light traces mass assumption or anything else about the mass distribution far away from the galaxy, from the multiple images here, is actually driven by additional model assumptions that we make in order to reconstruct the global distribution of the masses. And last but not least, what we find quite interesting, have a look at the feature matching that we did. It seems that we have relative small rotations between these multiple images. And now the question is, how well does the thin lens approximation actually do? And if we take a look at an older version of a free-form reconstruction that is on a global scale, then we see here in these really reddish colors that there are a lot of external masses around this multiple image configuration here, and they are put there in order to get the shear, the local shear and the global shear right, based on the choices, on the feature choices that we made. And the question here is, do these have an optical counterpart? Is there some light as well there? Or is it just ghost dark matter clumps? And the point here that I want to make is, if we have 3 shearings in a row and a scaling, this can mimic a rotation. So this might be a hint that we are actually dealing with a thick lens, a 3-dimensional lens, and not a thin lens, if we do not find any optical counterparts for these additional masses that are put here in the global reconstruction. We can also add this arc B, this system B here, in order to constrain the outskirts a bit better. Then, of course, we get more information in this region here, so the additional masses here vanish, which is also quite interesting. But still, the direction in which these additional masses are then shifted remains the same to get the shear right of these datasets. And last but not least now, we can ask, can we do all of this without dark matter? And there was a team that tried to do this, but again, in the thin lens approximation in 2 dimensions. So they took the stellar contents of the galaxy, the central galaxies, and the gas content based on the X-ray signal. And they found no matter what we do and how we scale it, and even if we give a mass to light ratio that seems to be on the verge of not being feasible anymore, we cannot reproduce this lensing configuration. But again, I'm asking, if we open up for a 3rd dimension, may we be able to do it without dark matter? This is a question of a follow-up study that I would be really interested to do. And at last, this work also used this configuration to refute Mond, but their argument was that the total mass distribution here should be a spherically symmetric distribution of the size of this Einstein ring here. And then they arrived at an acceleration scale, which was in the Newtonian regime, and this was their argument to refute Mond. But I think that this argument is not valid, and we should take great care of including this dynamical study here, and to see whether Mond is actually able to reproduce this galaxy dynamics, and in how far we can really understand the dynamics and the lensing signal with the least amount of dark matter that we really need. And because it's time to wrap up now, I would like to summarize and to give you the take-home message that from strong gravitational lensing, as far as we found out, the most important information, or the only information that we can actually get, is at the positions of these multiple images. And the farther away we go from the multiple images, and the faster the mass density profile changes, the less we actually know what is there. And the farther we go and the less we know, the more our model assumptions take over in order to reconstruct our data set, in order to reconstruct the global mass distribution. And I hopefully convinced you that Abel 3827 is a really nice test bed in order to join forces to see whether Mond could actually describe this cluster, and hopefully to also see how much dark matter do we really need if we want to impose dark matter. Thanks a lot. Happy to take questions.
Thank you, Jenny. Now it's time for questions. Yeah, Pavel, you can go ahead.
Well, thank you. I was actually just clapping, but I can still ask a question. So hello, Jenny.
Hi, Pavel.
Well, it was really a wonderful talk, very clear, and thank you for this explanation. The four massive galaxies at the center of this galaxy cluster are probably up to 10 times possibly heavier than we think they are. So do you see in any, and the reason for that is because they would be full of neutron stars and black holes, because when they formed, the galaxy-wide IMF would have been top heavy, and I think we might have emailed again about that at some point. But do you see in your data analysis any evidence for that you're actually dealing with heavier lenses than than one might think? Than the standard assumption?
Yes, I mean, in principle, what we found with our lens model independent approach is that we cannot make any statement about the mass of these galaxies, and that this is more or less driven by the models, because I would say the best information that we can get from lensing is at the positions of the multiple images. I mean, and then there is, I guess, there is hardly any visible dark matter, any visible luminous matter in the way, otherwise we wouldn't see these images. So there must be just like, I mean, maybe in the luminous sense, black holes, but they can't be, because then they just disrupt the multiple images, then they're not smooth enough. So it should be some gas content or something like this that we are actually probing at the multiple images. And now, if we want to make an assumption about the masses of these individual galaxies, yeah, they might be heavier than we expect, because this means if we have more heavier galaxies, we can reduce the amount of dark matter underneath it in order to explain the lensing signal. And something that I think hasn't been explored too much yet is these lens-lens coupling effects, because people usually use this thin lens approximation, so they just integrate over the line of sight until the lens plane and then towards us. But if you have a really close by two sets of galaxies, or two sets of really heavy masses, you have to non-linearly stack this lensing effect. And this could actually mimic, I mean, two heavy masses if you just project everything onto a thin lens. And so I think this is why I'm opting for, we should have a look at the three-dimensional structure here, because then we might be able to reduce the dark matter halo and to just increase the masses of the galaxies, as you say, by hopefully just the luminous content that is too weak to be observed for us. That would be my hope.
Thank you. Thanks.
Any more questions?
I'm also happy to answer questions on the Discord channel or via email, whatever you prefer.
Yeah. Okay, Sarji, you can ask.
Yes. Hi, Jenny. Thank you for the talk. It was very nice explanations. So this lensing system, Abel, I already forgot its number, but 387. So that's at, you said, Redshift 0.1, right?
Yes.
So we have a relatively good idea of what sort of the spatial distribution of it is, because it's relatively low redshift. Is this something that can also be sort of applied to sort of farther out galaxy clusters, or would the uncertainties in the sort of redshift and distance be prohibitive there?
That's exactly the point. I mean, as I said, that you need an extension along the line of sight that is relevant and non-negligible. And for most of these galaxies at higher redshift, it's quite hard to measure this extension along the line of sight because of the redshifts and because of the precision of the redshifts. And on the other hand, I mean, they are too far away, so the lensing effect is really just based on a pancake and not on a Belgian waffle or even on something thicker. So this is just a unique configuration, and I think we need more lenses in the rather local universe where this extent actually makes a difference.
All right, I see. So is this sort of like the most pronounced system we know, or are there different like thick lenses that we know of?
So far, I think, I mean, we stumbled over this, and it took me like a few months because I thought something is not right in this cluster, something is weird. It has been analyzed by a lot of people, and we were the first to think about this three-dimensional structure. The lensing community is not too happy with it, and they question this, and they rather, I mean, we made a prediction. If there are optical counterparts, we can still do it with the thin lens approximation, but so far, I think this is the only one that I've seen so far. And I guess this is why people still stick to this two-dimensional thin lens plane approximation. And people, I mean, now it's coming up that we include the three-dimensional ones. People are developing algorithm, but this hasn't been done for like, I mean, until the last 10 years or so, 5 to 10 years.
I mean, yeah, also realistically, even in the thin lens approach, I've always wondered if there's sort of this dark matter distribution that is assumed, that it's sort of this, two-dimensional plane instead of a reconstruction of some three-dimensional like space.
Yes, this is definitely something. And if you take a look, Massimo Meneghetti, he had really great simulations about, okay, the thin lens approximation, but he assumed spherically symmetric clusters. And then he broke up the symmetry for elliptical ones, and then even for elliptical ones that change the ellipticity over the scale. And all of this showed that you can reduce the amount of dark matter by quite a lot by just making your lens more complicated than a simple model. So I guess the same applies for the third dimension.
All right, thank you.
Okay, Luis, go ahead.
So thanks for the nice talk. So you said Abel 3827 is what, 5% of the distance between the roughly. So for a more distant lens, let's say it would be only 1% of the distance. Could those effects still be important in terms of guessing the mass, or the thin lens then starts working well enough for that?
The farther out you go, the better the thin lens works. And based on the other ones, I mean, take a galaxy at redshift 0.5. This is the standard case. And at redshift 0.5, you have really a very small, you have a pancake. And this one, I would say, is a Belgian waffle. And
it's okay. Yeah, thanks.
And I guess this is why it took quite a while to come up with this idea in the first place, because people were used to lenses at 0.5.
Great. Great talk by Jenny. So we can move on to our next speaker, who is Robert Monjo. I hope his health is good and he will be able to deliver his talk. So Robert, he is from St. Louis University, and title of the talk is Hyper-canonical Modified Gravity from the Large to Small Scales. Okay, Robert?
Hi.
Yeah.
Can you listen to me?
Yes. You're audible.
Okay. One moment, screen share. And because this occupying this.
You can go in the.
No. Yes.
Yeah, this one. Yes.
Yes. Perfect. So the motivation of this this talk is to analyze the problem of the current problems of the modern cosmology in terms of geometric perspectives. As you know, it's usual in physics study the astrophysics and the observations according to pseudo-Riemann manifolds, that is the intrinsic perspective of the metrics. But from geometrical disciplines, as differential geometry is also useful, use the embedding techniques in upper dimensional manifolds, in which we can understand the problem, the dynamical systems as a parametric functions within this space. So the problem of the cosmology is understood as a dynamical system that can be constructed in a natural way according to this embedding technique, in contrast to the general relativity and the Freeman-Robertson-Walker metric, Freeman equations that needs to set by ad hoc a metric with homogeneous space and an isotropic and a scale factor that is set to be in this way, and so it's a election of coordinates. So as you know, the spatial curvature is not a geometrical invariance in Lorentzian manifolds or in pseudo-Riemannian manifolds. The geometric invariance is the Ricci scalar. So alternative, we can choose other coordinates, but using the extrinsic perspective, that is, taking an example, this most simple example, that is an three-sphere with linear expansion, that is an hypercon. So this is a hyperconic manifold embedded into a 5-dimensional flat Minkowskian space. And the metric is this one, is the second line, that is only consistent with general relativity if this is considered valid for local. So the metric doesn't depend on the matter content. Matter content only modified perturbations over this metric, this background metric. So is an independent metric on the general level. And with this idea, we can define an hyperconical modified gravity as perturbing this metric. So we need to first solve the general relativity for the differences between final Riemann curvature and the background Riemann curvature, or the Ricci curvature of Ricci scalar. And when we have the solution, then we need to change the coordinates according to the extrinsic perspective, because if we have a dynamical system, the measures like space and acceleration depends of the observers, depends of the system. So applying this change of coordinates, we obtain a fictitious acceleration. And the result, the theoretical result, is a very similar phenomenon than Mond, but the Milgoranian acceleration can depend on the mass distribution. To check this, we consider three kinds of masses: the solar system, a galaxy, and a cluster. And well, the behavior is similar to the observed one. We observe a flat curve, rotation curve for where expected, and well, also is compared with observation, as we can see in the following slides. Other property is the gravitational lensing. So this modified gravity can produce also similar effects like dark matter, but without dark matter. And comparing with observation, specifically supernova curves, cosmic chronometers, rotation curves, galaxy clusters, also with X-ray gas galaxy clusters. We obtained the following observations. For the supernova type 1 curves, we obtained the luminosity distance and the fitting of the theoretical models of the ΛCDM and other, for example, the Milne-Coastin model, the Melia-Coastin model, and the hyper-canonical model. And the result shows that they are compatible with observation and very similar to the standard model. Especially the hyper-canonical model produces this the same results than the ΛCDM. And in this case is the angular diameter distance with other observations that also are compatible. According cosmic chronometers, the linear expansion is only compatible with one kind of data, that is in the model-independent data. Model-independent data is compatible with linear expansion, but other data like baryonic acoustic oscillation or from several sources show more preferences to the acceleration, to the ΛCDM model, but also the hyper-canonical model changing the coordinates also produce the same curve than the standard model. So it's a problem of coordinates. And for the galaxies, for the galaxy rotation velocity, we can reproduce the baryonic Tully-Fisher relation with a very good shape. So it's a reproduction of the Mond theory, but with a not exactly constant Milgramian factor. And this is the interpolation function for 60 galaxies in terms of radius and orbital velocity. And the result is good in comparison to the Mond theory. Well, for clusters, the advantages of the hyper-canonical model is that can also to reproduce the cluster radial acceleration anomaly with the same relation than the galaxies, according to the hyper-canonical modified gravity And for example, this line is the Mon, the line blue, and the line gray is the hyperconical modifier. And the two parameters that we are using for this modified gravity are not actually free, but depends on the mass density of the clusters. So we are happy in this because any is free in this model. Also for the hydrostatic equilibrium, for X-ray gas, for example, from a half megaparsec or a half megaparsec, we obtain a good result comparing the modified gravity expectation compared to the observations of the inward gravity needed for this hydrostatic equilibrium. Also for the rest, this is a complete set of 5 galaxy clusters with a complete masses profile, and this is a set of 12 galaxy clusters. Well, according to all these results, our idea is that according to geometrical perspective, using the most simple idea of linear expansion and changing the coordinates according to the moving observers, we obtained an apparent radial inhomogeneity that is assimilably to is assimilated as a fictitious acceleration with this change of coordinates, and this leads to local general relativity. That means that general relativity is only valid over this background metric instead of the flat Minkowski metric. And with this, we can predict this kind of acceleration very similar to the dark matter phenomenology and also the dark matter dark energy for the acceleration of the universe. And the dynamics for galaxy, dynamics for clusters, the hydrostatic equilibrium, the weak lensing, the gravity weak lensing. But the future works needs to be deeply analyzed for CMB and baryonic and the Big Bang nucleosynthesis, and also for the large structures formation. So we need more work, but we are happy that the most simple idea can be also adjusted to the observation. That's all. Thank you.
Thank you, Robert. So do we have questions? Yes, Indranil.
Can you go back to the slide where you're showing for different masses what like the rotation curve would look like and the anomaly with the Newtonian case? No, I think it was the slide before this where you had like also the one solar mass case.
Yes.
No, you had a slide where you were showing the one solar mass case and the rotation curves for that.
What slide is I?
Just for one solar mass, so not galaxy scales, but
Okay. Do you mean this
yeah,
one?
exactly. So here,
Okay.
what exactly is the prediction for like the case of m equals 1 m sun? So that's the green curve, right?
Yes. In this case, the prediction for the solar system is that we can expect anomalies for 10 the power of 4 astronomical units.
So like once you go beyond, so the prediction is that once you go beyond about 10 kilo AU, the rotation curve becomes flat.
Yes.
Is that true even for a one solar mass, like for a star inside a galaxy, or do you have some analog of the external field effect that plays a role in that case?
I'm not sure, but I checked that these range correspond to the Oort cloud.
Yeah, so, definitely it corresponds to the wide binary sort of regime. But is this like? But how does it work for a star inside a galaxy?
I need to check, but I think that and we need to compare with more concise observations to constrain this model for this range. But by now seems to be compatible.
Well, I mean, it depends on like the extent of the deviation you predict on that scale, right?
Yes.
Okay.
Yes. We can check later if you want.
Any more questions? Any more questions we have? Yes. No? All right, Robert, then. Thank you for your talk. And now we are moving to our next speaker, Shiva Dwivedi from Christ-Teamed 2B University. And his title of the talk is Effective G in Modification of Newtonian Gravity. Yeah, Shiva, whenever you are ready.
Yeah. Is the screen visible and am I audible?
Yes.
Right, okay. So I'll be talking about variation of gravitational constant in this theory called modification of Newtonian gravity. And this is my master's project at Christ University, which I'm working on and continuing my education over there. So I'll dive straight into the topic. And, yeah, so we based on the observations of all the galaxies and clusters, we very well know that the outer skirts of the galaxies do not follow the predicted or existing Newtonian laws and Keplerian laws. So we come up with the idea of dark matter over there. And although there are very much evidences in support of dark matter, and many experiments designed to to detect these dark matter candidates, they all have given negative results so far. And then we start looking into particular modifications towards the gravity theories. And one such theory is modification of Newtonian dynamics by Milgrom. And there we get quite good data observation and the theory prediction. The results match very well, but the
concept in MOND that the ubiquitous occurrence of A naught in the MOND was quite ad hoc. And although it predicts the flat rotation curves and other problems in the existing models, gravity models, this ad hoc introduction of A naught was not, A naught was quite disturbing. And then in 1994, Professor Sivaram came up with this idea of modification of Newtonian gravity, where the assertion is the background self-energy density, the background repulsive dark energy density should be equal to the self-energy density of the universe which we are talking about. And in that case, we get this A naught, that is 10 power minus 8 centimeter per second square, quite naturally with that assertion. And upon following up the calculations, we get that we need to modify the Poisson's equation of gravity. And upon bringing in the necessary substitution and adding a gravitational self-energy term in the Poisson's equation of gravity, we get a modified equation. And also, just to make a remark that here dark energy is completely included in the model, and upon including that factor, we get another term on the right hand side of this equation, on which I will not be talking. We'll be continuing just with the self-energy term. And upon solving this particular equation and determining the potential function, and then we get this flat rotation curve quite naturally, and it matches the observation and the predictions with the MOND as well, where the requirement as suggested by Milgrom was that it should be scale invariant, and the flat rotation velocity, or the velocity, is the fourth power without any distance dependent function. And these are some of the data which the group has plotted. And yeah. So also, when we are talking about such a modification, there is quite a certain possibility that gravitational constant also should be looked upon at. But before going into that particular aspect, we must look at this figure where if one tries to look at the modification of a theory or any particular constant as such in terms of distance, then it will not work as well, because we can see the dynamic mass and the observed mass. It is not a function of distance. It is different for different type of cosmic objects which we are looking at. So any modification which is being done should not be a modification with respect to distance only. And in Mong, we talk about modification in terms of this A naught, where the distance fall, where the acceleration when it falls below the critical acceleration, that is 10 power minus 8 centimeter per second square, the Mong effects start to take over. And upon doing the calculations, we arrive at this particular function of distance. This is not a particularly distance dependent function, but it is a function of R max, where R max corresponds to the distance, or the maximum distance, where the acceleration is less than A naught. And yeah, there is a eta parameter which is brought into the equation to take care of the ever increasing function at higher distances, because this is a function of x of a distance, and after a certain point the distance keep increasing, but the gravitational constant needed would be the same to account for the flat rotation, and that part is taken care by eta. The mathematical formulation of this eta is still under investigation, but so far it is believed that it is a negative exponential function, which will be depending on distance and certain other parameters as well. And yeah, upon going beyond the distance of R max, or say beyond the regime of A much less than A naught, the gravitational constant starts to vary, and it increases. A fair calculation in Milky Way galaxy showed that it was around 9 into 10 power minus 11. So yeah. And then we also look at the maximum variation in the gravitational constant which can be brought in. So this was the data matching and work done with respect to the gravitational wave data, work done by a team at ICTS. So they were looking at a merger of two neutron stars, and upon receiving the data, while matching the theoretical template and the gravitational wave phase, they found that there is a maximum or a limit on the gravitational constant, which it can vary in cosmic time. And yeah, so the lower mass limit and the upper mass limit of neutron stars were determined already, and they assumed particular equation of states to do the calculations. And upon doing that, we get such figures where the vertical dashed line is the allowed mass range of neutron stars from the current nuclear equation of states, and the vertical solid line is the maximum range of range in which the gravitational constant can vary in that particular time limit, in cosmic time limit. And upon doing it further, the fractional deviation in gravitational constant was observed as shown over here. The point to be noted here is the minimum deviation is more or less constant, but the maximum deviation, it changes with the epoch of the phase which you are looking at, and also at the cosmic time scale where we are looking at. And the idea is, if we are looking at more lower frequency gravitational wave data, we can see more variation into the gravitational constant over there. And such a variation in constant with cosmic time, it suggests that these constants are not universal constants, they vary with respect to cosmic time. And the parameter eta which we are talking about, which is still under investigation, is supposed to take care of such variations as well. Although the acceleration regimes which you are talking about are quite different, the G wave merger is much higher than A naught, but still the eta parameter is supposed to take care of that. And yeah, so over here the teams tried to look at the rate of change of gravitational constant with respect to particular certain observations which were made using different data sets, and the rate of change with cosmic time was observed as shown over here. So this is about variation of gravitational constant with cosmic time and the distance as well. And we're talking more about MONG. We have maximum MOND. There were in other modified theories, we had certain drawbacks where we could not predict the large scale structures, the limit on large scale structures, but with the concept of minimal acceleration in MONG, we have the data and the calculations quite well in observation, and they match pretty well over here. So that is all from my side.
Yeah, thank you, Siva. Now it's time to take some questions.
Yes, hi.
Hi.
I have a question.
Yeah.
Yeah, go ahead. Yes.
Well, does MONG make any prediction related to the tidal tails of star clusters?
Okay. Yeah. So the team is trying to look at the tidal disruptions in the Fornax cluster, and the work is still under construction. We have positive results so far, but since the work is not completed and it is not concluded yet, I haven't included it in here. But so far, the analysis done in the case of Fornax cluster has shown positive results. It explains the tidal disruptions and the disrupted morphology in the inner part of the clusters.
Sorry, but I was referring to star clusters in the galaxy, not
Okay, inside.
cluster.
So inside the galaxy, we haven't looked at that part yet. Inside the galaxy, the stellar clusters, not yet.
Well, because probably, as you know, MOND finished D predicts that the leading tails of star clusters should be more populated than the leading trails. And we have made a study of about 200 open clusters in the galaxy that shows that this is not really the case. So, in base to our empirical study, MOND is ruled out. But I don't know about MONG because you haven't you haven't done any prediction on that aspect.
I haven't looked into that part yet. Maybe team has done some earlier work, but I'm not aware because I joined the team quite recently. So yeah.
Thank you.
Okay, one more question from Pavel.
Yeah, I think I should just say something to Johan's statement just now. The tidal tail asymmetry in Mond is a correct description, as Johan just said, but one has to be hellishly careful in using the data. So the 4 nearest clusters, which have been studied by Gaia, show this asymmetry, and 6 different teams looking at their data show this asymmetry. If one goes to further distances, the problem is that there are biases, observational biases in terms of which tail is further, which is nearer to the sun, and in combination with the Gaia uncertainties, which of course increase with distance. So there, I think one has to be very careful, and any signal is quite easily washed out with further away clusters. So I just wanted to mention that concerning Mond.
We have been very careful, and we have studied not 4 clusters, but almost 200 clusters. And the distribution is quite Gaussian, and even you have a little bit more clusters having the trailing tail more populated, slightly more populated than the leading tail.
Yes, but
we are quite sure about the results and about the conclusion.
Undeniably, the uncertainties increase with distance as well as the biases, and that means you're adding noise to the signal. So I think one has to be very careful there. We are doing our own.
I can send you. Well, in fact, I send you the results, and you and other 2 people in this meeting, and I don't know about any answer, but the results are there for any criticism or any specific study scrutinizing.
Yes, I just comment, it's easy to shoot down a theory with bad data, so one really has to be very, very careful there. But we will look at it. Thank you. Yeah.
Thank you.
Any more questions we have? If no, then we thank our speaker, Siva, and we now next move to the poster session, and our speaker is Fizake Kalam Sangeeta. So whenever you're ready, and it's our last event, and we will meet tomorrow at the given time.
Am I audible?
Yeah, you're audible.
And my screen is ready to present. Is it okay?
Yes, you can now do the full screen.
Yeah, here internet connection is a little bit unstable, so that's why I'm asking.
All right.
So can I start?
Yeah, you can go ahead.
Hi, my name is Sangeeta Kirkekalam. I'm from Kerala. First of all, I would like to start my presentation with a quote. Look up at the stars and note down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. This is a quote of Stephen Hawking. To boldly go where no one has gone before. So I'm here to present my master's thesis, Multi-Wavelength Investigation of Star Formation Activity towards the Galactic Cloud G13.89 -0.47 under the guidance of Tina V.S., Postdoctoral Fellow of Max Planck Institute of Radio Astronomy, Bonn, Germany. So as we know that it is still unclear that how the physical process that lead to the formation and evolution of massive stars work. So here we are studying the individual region of G13.89 -0.47. It is located at a distance of 1.9 kiloparsec. Previous studies identified that there are 14 infrared dark clouds and no masers are presented there. So these are the sign spot of massive star formation in that region. So we are using multi-wavelength observation from infrared to radio wavelength to comprehend the many aspects of massive star formation. So information associated with these regions are collected from Spitzer Space Telescope and NVSS VLA Sky Survey. So here you can see the mid-infrared maps of the target at 3.6, 4.5, 5.8 and 8 micrometer. From the maps, you could see a bright emission surrounded by a dark patch, that is infrared dark cloud. There are greater number of point sources in 3.6 and 4.5 compared to 5.8 and 8. It is because they are of shorter wavelength and it represent the emission from warmer dust and also from stellar photosphere. But in the case of 5.8 and 8 micrometer image, the emission is only from warmer dust. So in order to study the outflow, signatures of outflow, we have constructed a flux ratio map. A flux ratio map of 4.5 to 3.6. The ratio is found to be 1.5, which is actually for jets and outflows. So in the flux ratio map, we can see a flux ratio excess towards the center and its morphology is arc-like. So as we know that the stellar objects and H2 regions are the precursors of star formation. So in order to study and classify young stellar objects, we have constructed a color diagram. It is a perfect solution for classification and studying young stellar objects. So in color diagram, we have taken the differences of magnitude between 5.8 and 8 micrometer images on x-axis and differences of magnitude between 3.6 and 4.5 on y-axis. So from this, we find a total of 56 young stellar objects, of which 23 are class 1, 16 are class 2, and 17 are class 1 or 2. Then here you can see a distribution of YSO over 8 micrometer image. From the figure, you can see that distribution of YSOs shows an asymmetric distribution, especially towards the eastern side. So as the bright diffuse IR emission is also observed on the eastern side, so this could indicate a probability of density gradient on eastern side, and also the presence of a star formation region also in that side. So in order to get an idea about massive stars and H2 region, we have used radio continuum image from NVSS survey. So here you can see an image from NVSS survey, and you could also see a bright emission at the center. So if we consider the in the case of a massive stars, the blackbody radiation peaks at UV. Then the UV photon ionizes the surrounding environment and other forms a ionized hydrogen plasma. So the Bremsstrahlung radiation from plasma can be used using radio telescope. Then to know the spectral type of the star, which is forming in the region of G13.89 -0.47, we have calculated a Lyman continuum photon rate by using this equation. In this equation, F nu is the flux density of H2 region, TE is the electron temperature, which is plasma temperature, which is assumed to be 10,000 Kelvin. Then nu is the frequency, which is 1 gigahertz, and d is the distance to the source, which is already given 1.9 kiloparsec. By calculating this, we get 3.2 into 10 raised to 46. So comparing this value with the 0 age mean sequence value, we get it as a 0.5 star. So our current work is to use the spectral line data to investigate the structure and kinematics of the molecular cloud associated with this region and to extend our study into a large region. So that's all about my presentation.
Yeah, thank you, Sangeeta. Any questions? Yes, Pavel.
No, sorry, I was just clapping my hands just to show.
Okay, okay.
Right,
Oh, great.
but this is very interesting, and I'm particularly interested, of course, in in the MECL relation, as we call it, so massive star embedded cluster mass relation. Do you see evidence for that, and whether the IMF might be different if the metallicity and density of the star forming of this embedded cluster might be different to what we see more nearby, right? So I don't know if you've looked at that by any chance. Sangeeta, we can also talk. I gather you are here in the Max Planck Institute, so it's basically you are next door, right? So we can also talk.
My guide is in my Max Planck Institute. Now I am admitted to University of Cielona-Garra for my PhD. I'm going in December.
Okay.
Any more questions? So I guess we don't have any more questions. So thank you, Sangeeta. And thank you everyone for joining our today's session. We are closing this online session, and you can discuss in our Discord server, which is the link is mentioned in the YouTube video description link, as well as you can find in the email, or also it is mentioned in the website. So thank you again, everyone. And I expect that we are expecting that you will also join tomorrow. Tomorrow we have session 3, and the session would be on cosmology and large-scale astrophysics. So for now, we are ending. So thank you, everyone. Bye.
Recording stopped.